Oh, looks like it's saying the show's got to start. Better do what it says.
Like Terry.
I wish it was all automated like that. Make it a lot easier. Just program it. Oh, we got a few people out there. I can see Carl. I can see Stevie. Yeah, where's Mute? Is he hiding somewhere? Dave came late. That's okay. I see Glaby out there. Elmigs. Peter's lurking out there too. Renee Me. Miro. Oh, you haven't got a spanner yet, Miro. Oh, Sean. Sean's building a drone. Can't you just buy them? Oh, you got to build one. I thought you just buy them straight off the shelf. Well, we do have John and Paul here somewhere. I don't know if Paul's got... I was just about to say the same thing what you just posted. I was just about to say. I wonder if Paul's got a scientist for the day.
I do. I'm just about to change my name.
Okay. Today's scientist, D something something B something something, was a Swiss mathematician and a physicist who applied his math skills to the topic of mechanics, in particular fluid mechanics. Okay. If I knew what fluid mechanics was in comparison to...
That's the way fluids work.
Oh, okay.
The way fluids move.
Okay.
I'm just going to go to the kitchen. Someone's calling me.
What are they calling you?
Good one, Terry.
It's the same thing as when somebody says, I'll call you a taxi, or I'll call you an ambulance. You're an ambulance. Oh, Elmix has come up with somebody. Well, I can't confirm or deny the correctness of that answer, so I have to wait. You're not copying anyone, are you, John?
No.
Nah.
Oh, I wouldn't do that.
No, you wouldn't do that.
No.
Well, he's Swiss, so his name would have to be... I don't know what names are... Are you saying that name could be a Swiss name? Daniel Boone. No, Daniel Boone. Daniel Boone was... I'm trying to think of the theme song.
Man.
Yeah, that's it. I was trying... You don't sing it. I'm just trying to think of the lyrics. Yeah, I was just trying to think of the lyrics for it. Well, I haven't got many videos. Sorry, John?
Sorry. No, you're right, Terry. Go on.
I was just going to say, I haven't got a lot of videos lined up at the moment yet. I've got your old favourite, Lindsay, and I've got a Bob Nodell's Gas Attack link through from Blue did this. It's 19 minutes of it, but he did do a separate one that's edited to 12 minutes, so Blue must have edited a part of it out. So we can either watch the unedited version or we can watch Blue's edited version. So
the Elmigs is right onto it. It is Daniel Bernoulli. There you go.
Not Daniel Boone.
Not Daniel Boone, no.
Okay. Phil, Alan's not here at the moment. So, and this is my stream, Phil. You keep forgetting at the moment. At the moment, I'm streaming through Alan's channel. I've got your favourite Lindsay, Phil. I may as well get on with it then. What do I need? I need that. You'll need that. You'll need that. Okay. I think it's. I'll show it in here. That way you can see which one we're up to. I'm trying to remember now. So the one with the red, we've already seen that one. And then this one we haven't seen. That goes for 18 minutes. So we're still, oh shit, we're still a fair way behind.
Yes, he's pretty prolific at producing the derp, isn't he, Terry?
Yeah, he is.
He's on a roll.
The lie about magnets and Earth's magnetic field. That we could watch.
God.
Yeah, that one comes after the 10-minute one here. I thought we'd seen one of these. We watched a short one and a long one. I remember we watched a short one and a long one the other week. Might have been the same one. I remember that. And then we watched this one, Our Universe is Right. Big science discovery. I wish his titles a bit more correlate to his topic. I think we might jump to this one. How far is the moon really between phases? I think that one would be interesting. I think that one might be alright. We'll go with that one. How far is the moon really moving between phases? I'll grab that one.
That's.
Yeah. Okay. Oh, need sound. Aren't you going to comment on that first statement?
Flat Earth science, that's a misnomer.
Yeah. I know you can only get it. You start some of these videos and you only get into the first two words and you go, that's it.
Or you might not. Which begs the question, Lindsay, how do you know what's in there?
Yeah, that seemed a bit of a conundrum, that one. You can't get in there.
Can't get in there and we can't see in there. So how does Lindsay know what's in there?
Yeah, but he's saying that's what we see from this side. Oh dear. I don't think he thinks these through sometimes. Oh, Carl said he's deaf. Why are you deaf, Carl?
Ah, no sound.
I don't know. Is it? Just look. I might have it not on.
Anyway, working on the moon. Where shall I start?
Sorry, Carl.
Now, this is what the moon's doing. Basically, this is a cone.
They want to hear Lindsay's derp as well, Paul.
Oh, do they?
Yeah.
Yeah, well, they better have protection.
But represented as a pyramid. The Egyptians have left it all for us. The sun at the top of the pyramid. These are the 4 pillars the earth is supported on, because up here is the sun.
Carl
Where
said,
the sun
damn,
is,
now I
is
can
the
hear
black
him.
hole. Where the black hole is, it's amplified our whole realm. Earth is created from this black hole, from this realm.
What?
But up in this centre of
Earth, what? Created from the dark hole or the realm? Or
A black hole. A black hole.
Right.
You know, like, apparently they're magical things that can create stuff.
Not from what I thought.
above the Arctic is where all this magic is. It's all going on up there.
Yeah, magic.
Yeah.
It gets sucked
Yeah,
up
I
there
told you.
Yeah.
and it gets sucked down there. This is the cross. Plato even draws a cross in his Timaeus. The cross that's in there.
Does he?
2 pyramids basically.
Citation.
This is represented
music.
by the 5 tiers, 6 tiers of the de jure pyramid in Egypt, Cairo. Or
Why does that remind me of the pyramid scheme things when you draw things like that?
Saqqara
It's
or
the
whatever.
healthy food
And
pyramid.
then you've got
Yeah,
the
the
other
healthy
pyramid
food
up
pyramid
here,
too,
flipped
yeah.
upside down. And this is where you get a negative field coming up here, or low high pressure.
Low high pressure.
Yeah, low high
You've got a
pressure.
magnetic
Yeah.
field down
Or is
here.
it high low
An
pressure?
electrical field up here now. And it gets sucked back down there, creates all the pressure down into there. This gets all sucked back up into there. So these are the planets.
Which
One
ones?
up here. We're looking up through there. And
Did he draw enough planets? I think he's missing a few.
Yeah, I think he's only got the Galilean planets there.
Oh, okay.
Yeah, need a couple of comets too.
what the moon does is it winds around down all the way down to full moon. This is Earth down here. Full moon.
I know what winds. He's winding us up.
Yeah.
New moon when it goes back up. Now, because the moon's winding down, it's on this diagonal winding down, there's a big torus field in the centre of Earth, right? It turns everything, our whole system turning from this centre point, all projected out. Just like a clock, everything's projected at the hands of a clock, or throw a pebble in a pond and see all the waves go out. Or
No,
move
not
out.
the clock. Yeah, I can understand the pebble in a pond type scenario, but not. I don't know where the clock might come from.
Creation's been amplified outward, spiraling out. You find our Earth has grown outward, spiraling out as it's grown, all from the centre, primordial stone, whatever.
Primordial
what-
stone.
So, what evidence do we have that the Earth is growing?
It grew from a seed, Terry, a primordial stone.
Yeah, don't forget whatever.
Who watered it?
Yeah, I was wondering that.
So this cross is basically in here. That's where the plasma is created under pressure. Type.
Plasma? That's a new one.
Yeah.
I don't think I've heard plasma before. I'm sure I haven't heard plasma. Not. Okay, that's a new one. You'll have to explain that one, Lindsay. That's a new one.
Magnetic field created from the Earth. It's created its own closed system from the magnetic field. Once the Big Bang happened and created the sun, you get the magnetic field. That's the dome, the magnetic field. Nothing solid. Christianity.
Isn't that a bit of a thing with trying to use something like the Big Bang into his model? Because that's something that's more for us than what we attest to or we come up with, and now he's bringing that into his. So you can't just cherry pick something from that is true.
No, and what you saw there, Terry, was literally a perfect example of a hand-waving explanation. He hand waves away the explanation. Like, did you notice that? That while he's talking, he's waving his hands around the thing as if that explains what everything is. So that's what they mean when they say he just hand waved the explanation away. Yeah.
I'll have to play it again, just that bit.
It's created its own closed system from the magnetic field. Once the Big Bang happened and created the sun, you get the magnetic field. That's the dome, the magnetic field. Nothing solid. In Christianity, it says it's unscratched. Can't scratch. It's like a force field. It's like a magnetic force on a magnet, inverted, and we're inside there. So this is going on in here. Planets, so magnetic, electric, electron, proton. Sun's a proton, moon, planets are electrons. So the moon...
It's just so disjointed. He just pulls things out of his ass and like... He'll be going on a certain track and then it's suddenly like, whoa, hard left. And he brings up something else completely different and unrelated.
Was he separating the electrons from the neutrons?
Well, one moment he's talking about planets and the next moment he's talking about protons and neutrons. I mean, what the hell?
Yeah.
Yeah. They're a little bit smaller than a planet, aren't they?
Yeah, they are.
It's like a harmonic oscillator. It's all about frequencies. Frequencies is light. It winds its way up to the sun and new moon and then winds back down for full moon. Every month. Does the same thing. Like this. Over the month.
Yeah, perihelium, aphelium. Yeah, I've learnt that one.
The sun's magnetic field, the magnetic fields of Earth do over the year. So the yearly cycle and the monthly cycle.
Jinx said, is this about the 30th time Lindsay has gone over this? Yeah, he does. He's repetitive in some parts of his explanations, but then he throws things together in a weird way, and then he adds other stuff to it. So that's what makes it hard.
The moon's doing the same thing. So you end up with a cardinoid shape from my previous videos. But because it's winding down, it's going diagonally down. The sun doesn't move down, it just turns. It's going 50.
Phil said he's not feeling too good. Later, Phil.
Well, that's good. Yeah, I hope you get better soon, Phil.
15 degrees an hour. And this is the tropic region. That's the ecliptic. Planets, sun, moon, move around in that area. Which is right back here in the centre. Centre of Earth, centre of here.
I wonder if he actually picked up on the equinox thing we had the other day in one of his newer videos. I wonder if he'll actually bring that up or not. Some real stuff.
It's all around here. You can back that back up. Press that up. That's good for visuals, right? So because the moon is winding down past all the planets to get down to full moon, close to the Earth, because the Earth is negative, that goes positive. When it winds back, the moon goes negative.
Hey?
The Earth's negative? Oh dear.
Was it, the way he was moving his finger down, he was making it like the moon comes down closer to the Earth. Did you notice, is that what he was saying, that part?
Mm-hmm.
The Earth is negative, that goes positive.
Right.
When it winds back, the moon goes negative.
Oh.
To be attracted to the positive sun. It's just the way it works, the phase shifting.
Oh, okay.
Gas, you could say, to liquid, dissolved in the atmosphere. Don't see it anymore. It's not hidden, it's just dissolved. And it forms again. It's about
What?
atmospheric pressures as it comes close.
What? The moon dissolves?
No, the atmosphere apparently. I mean, this
What?
is just randomness. This is extreme randomness. He just cuts from one thing to the other flawlessly without even pausing.
Yeah, that's why, mate. Oh no.
Closer to Earth,
Oh dear.
gets more condensed into the pressure, magnetic field. But because it's not going around like this, it's moving down, across, diagonally. It's losing ground. It's losing ground to the sun. So the moon's only doing this. It's not until say 13, but that's actually doing that. And the sun's doing that.
Doing what?
So because it's that little bit slower, we're losing
Doing that?
this
Oh, okay,
much
it's doing that.
Yeah.
per hour because of the downward cycle. So if we take that downward cycle, add them all up over the month, or half a month, because it takes half a month to get down to there, another half to get back up, we take all that.
Yeah, he's insinuating the moon itself moves down in a month.
Apparently, I mean, if those steps of the pyramid represent the planets, apparently the moon's just roaring around the solar system.
Yeah.
Willy-nilly.
Yeah. That's like billiards on a table.
Yeah.
1.82, which is getting lost coming down the diagonal, add them up, it's going to give us a vertical measurement from there to there, how far the moon's moved.
Yeah.
So you go that
Obviously.
times 15 days from there to there, half a month. What does it, look what it equals, 27.3. It's exactly the same as a sidereal month, 27.3. I just found that out, I didn't know that. So I know I'm on to something. I can start coming up with these numbers.
He's on something.
Now, around here, it's 111 kilometres per degree around the equator, around the tropic area here. So we go that, every degree times every day over the 15 days. We're going to get this. 3,000 kilometres.
I can't read it.
What?
Yeah, I couldn't see what his math is on the. I can't see what his math's on the board, but it looks like he was trying to do it in his head. But I can't work out what math
He's saying that, like, you know, on the Earth, how every degree, if you move north-south, is 69 miles, right?
Right.
So every degree in latitude is 69 miles. Okay. Well, that's roughly 111 kilometres if you convert it into kilometres, right? And then he's saying that you multiply that by, what was it, 15 or something there?
Yeah,
and you get
15.
3,000, 15 degrees per hour. And so the moon, apparently, he's going to say, is travelling 3,000 kilometres in 1 hour or so. But that's if the moon was rolling around the surface of the Earth, which it's not.
That's going pretty fast.
So you'd have to speed up and slow down by his rotation going up and down.
So every degree
No, well,
is 1,100 kilometres. And we've taken all these times 15. That's how many degrees. So, but we're going vertically, right? But you know, you can see 10,000 kilometres from the centre there to the equator will be 10,000 kilometres up here because it's basically a circle. So use this degrees use the same degrees here for distance. I say. That's what I've used here anyway. So you know,
Okay,
degrees.
yeah.
So
You say.
that kilometres times that degrees gives you 3,039 kilometres. The moon
Get the ruler out for that one.
is moving 3,000 kilometres from new moon to full moon. New moon to full moon. It's moving within there. And I've got this earth here. Like I said, if it's 10,000 to there, it's 10,000 to here, but it's probably more like 9. I'm working on the divine number 3, 6 and 9. I thought it was 9. 9,000 kilometres to there then. We fly way down here. We're way down here. Got this realm up there.
So what is he, a lot of his assumptions are based on the numerologies that he's already got, and then he's trying to fit those numbers into his model. That's what it.
Yeah, it's reverse
what
engineering.
Yeah.
So, yeah, so there you go. It's moving in here. So, at the most, that's 3,000 kilometres to the full moon. But
From the surface. From the surface.
Yeah.
3,000 kilometres up from the surface. Okay.
Because it's written in religion and Egyptian, 1,600 furlongs. So, I'm not sure, but we're in a closed system. That just shows the moon's only moving that distance. From full moon to new moon. If we work on that
What happens on
degrees,
the other side?
and you work on that,
You got a technical question?
Yeah, what he's got 2 domes there, but what happens to the moon on the other side? Where is that?
No, there's
going?
not. There's not 2 domes.
Not
It's
two
a,
donuts.
it's a donut.
Oh, okay.
It's a cross section of a donut.
Oh, right, okay. Right.
Don't,
What?
we've got to get you up to speed on this flat Earth model of Lindsay's, John.
Righto, okay.
the measurements they've got. 1,100 kilometres. And I know the sun does that, the moon does this to the sun, down. It's the attraction to the earth, and then it's attracted to the sun. This is the Egyptian story of Thoth and the sun getting upset with the relationship between the moon and Jeb and earth. There's a two thing going on here.
What, jealous? It might be jealousy.
Just be careful you don't upset the sun, Terry. The sun might decide not to shine anymore.
Uh,
Doing along with the sun and doing along with the earth. Keeps coming down to the sun, leaving the sun behind. Keeps coming down to the earth, I should say, leaving the sun behind. So it's always winding up and winding back down. But it's always the same speed, whether it's between there or there. Well, that's how a clock works, isn't it? That time in there is the same time out here. You've got a clock arm coming out, tick, tick, just the same there as it is out here. It's the way our Earth works. Something else in my previous videos, I've been saying that we shrink away as we come out here. Because I'm trying to work to their ball, wonder how you get back to this point. But I've gone backwards. We don't shrink away, it expands. That distance from there to there is the same as the distance in here within these magnetic field lines. That is the same as that there.
huh?
That's 10,000, we'll say 1,000 kilometres there, it's 1,000 kilometres there. That's how it works. They'll all add up to the distance they give you around Antarctica. That's how it works. This also is connected to the Bible.
Oh, jeez.
You know,
he puts his
we-
finger,
you know,
he puts his finger to go right around it. So that's the distance that we're given to around Antarctica. What, that distance? I don't think it's
Terry,
that
we need a
distance.
count. We need a counter. We need a counter, Terry, or a
Right.
bell that goes ding, so
Yeah,
that every time he says, that's how it works.
right.
Ding.
Go ding.
We count it.
Yeah, okay.
Yeah.
Bible it says in those days were well, in those days they were Nephilim, but they speak of giants. Giants. These are giants because everything gets bigger as you head south. It's all relative to your position.
Everything's bigger when you head south.
Hey. Yeah, Terry.
Yeah, I'm bigger than you, John, because I'm more south than you.
Though,
Yeah, I know.
everything becomes bigger and bigger and bigger. And you'll find in religion that giants is always
Oh, wait a minute. Paul's further away from me, so even Paul's bigger.
mentioned was somewhere south. It's all metaphorical, the Bible and everything. Every time they mention something about giants, it's south, in the south of somewhere. You look it up.
South of somewhere.
South of somewhere, but there's always two meanings.
Yeah, south and
There's,
somewhere.
another meaning, the giants being the chosen ones of enlightenment, but it's referring to this too with the earth become bigger. There's guts. Now something
we
else. I saw a video, science video on TV, same old stuff, all rubbish and make believe, discussing the elliptic shape the planets take and all that. So they just stay on their tracks, they don't cross each other, going around. We set up in the sky on the elliptic plane like this, because the magnetic fields of the elliptic magnetic vortex, it has to be on an angle to get somewhere. It's going to sit level, it's not going to go up or down, is it? It's going to sit like that. There's always like that. That's perihelion.
Is he talking about the ecliptic plane of the planets? Slightly.
Who knows?
Slightly.
If it's facing that way, equinox, aphelion. There's the elliptic angles. The planets will be doing courses like this over the air. That's what it'll be doing. But at the same time,
washing machine going.
it's going
or
around.
something.
Yeah, it sounds like he's got something going in the background. It's not my fan in my tower this time, Paul.
No, I know it's not. You, Terry. Either that or the aliens have landed.
Oh.
Go do some probing.
Slightly, because you've got the black hole. The black hole's in the middle here with the egg. There's the yolk, the egg. So you have to imagine it not only tilting like this over the air, but turning as well. That's why science can't really get their head around what the hell the planets are doing. That's what it's doing. It's going around gradually, and then it starts going back up that way as it goes around. Just like the sun.
Kind of like the teacup ride at the fair.
Yeah, I was just thinking of something like that at the
Equinox, then keeps going up like this.
fairground, with the way the thing goes around like that. Yeah.
So, the North thing start doing an elliptic. The planets aren't really doing an elliptic. It's because the sun is a cosmic egg, and that's your reference point. Nothing moves faster than the sun. They don't pass the sun catches up. So if you take that planet there, for instance, look close to the sun. But because the sun is moving that way, quicker, they think the planet's going retrograding, going backwards. No, it's not. And because it's close to the sun there, all of a sudden, look, it's a long way away from the sun now. They think it speeds up when it goes around, passes the sun.
So
Alright.
what about the
It's
Earth?
the same.
The sun disappeared.
Now, you look at this, the sun's there, the planet's there, because it's down there, coming away from it, and coming close again, they think the planet's doing an elliptic, an egg shape.
We're talking about things getting larger towards the southern things, Carl. But that's interesting. Carl's got elephants the size of elephants over there in Africa.
But it's not. They're all getting confused with the shape of the black hole in the sun. There's a black hole in here. This is the black hole. The planets are basically around the perimeter. That's the ring of fire. That's how it works. The sun is the quickest to the centre of the pond, basically, as the waves come out. See, further away, comes closer, because the sun shoots past it. They think the planet's going this way, but it's not. It's the sun. The sun, right back there at the centre. It turns a little bit. Well, it has to. That's our 24-hour day. 360 degrees is a 24-hour day. And no Polaris and Sigma Octantis turn a little bit, because they are the sun. The sun. Polaris is up here. Sigma Octantis out there. It's reflected out there. So, although it sits like this most of the season, or like that, at the equinox it's dead level, it's not an elliptic. The egg, the cosmic egg, is the elliptic shape that makes these appear as though they're doing elliptic trips. There's the sun, see, close, further away, long way away from the sun. But in actual fact, it works the other way. The sun there reflects its light through this way.
Huh? What? I'll have to get on the booze again, I think.
I heard a Father Ted quote in my head when he said far and close.
So this is daylight.
Okay, Dora. You want to know what the ground speed of an unladen elephant is? Yeah, heading south or north?
See, the sun works. That's day. Shines back through this way. So you won't see the planets there, will you? Daytime. You'll see it up here. That's the back of the sun. You don't see it. Unless you get a telescope out, you'll see the back of the sun in there.
What? If we get the telescope out, we can see the back of the sun. Well, not at the moment, because it is night time.
Milky Way. The light in the Milky Way, that's the back of the sun. We don't see it back here at its source, we see it reflected. It's all a reflection, mirror image, out here in the sky. Flat Earth has all the answers. Because it's all
If you
spelled
make
out
it
by
up.
Egyptians, and it's written in Christianity, even Nordic, King Arthur story, Egyptians, Thoth, the Hermetica, all that spells it all out.
Three little
What's
peaks.
that? The fact the magnetic fields go like that, they will pull into the equator, the tropics like that, and science has gone and pulled them around, spun them around this way to make you think you live on a ball. Now it's all this shape, just so they can get a globe, so you can look at all the continents on there. But it should be drawn like this. But because it becomes so small, it's really hard
So where's all the continents then?
to get all the planets drawn in here. I mean, continents, just have a big drawing, you get them all.
That's one thing he hasn't done then. He hasn't actually done any comparison things like drawn the continents or anything yet.
Yeah.
Easily seen. But that's what Earth looks like in reality. I mean, this is probably a good idea just to draw your continents on there so you know roughly where they are. It stretches everything out so you can see them all.
Terry.
Yeah.
I don't think he should be worried about the continents. He should be worried about the incontinence.
Okay.
Yeah.
What, from all our laughter?
But there's no way you could use that ball to travel anywhere if you get lost. The magnetic field lines go like this. You follow that curve with your compass, and if you've got a gyro, you tend to go in a straight line if it's preset for this
You can follow that line with a compass or with a gyro.
area here. That's all I wanted to talk about in that video, I think. Thanks for watching. Thumbs up.
So the only bit out of all that to do with the moon moving between phases was that 3,000 mile calculation that he made up. Yeah. Okay. Made us watch that
So
whole
we got lost
video
on the way.
just for that bit.
Yeah. Yeah, you got lost on the way, mate.
Well, I think he did. Oh, stop share. There we go. I'll get rid of Lindsay. Oh, that's your Lindsay for now. 21 minutes and 22 seconds that went for. Okay, I'll get rid of Lindsay. How many questions you got or whatever, Paul?
I've got 20.
Do you want to do half and half again like we did once before? Because that seems to divide things up.
All right.
I don't think we're going to be going for 3 to 4 hours tonight by the look of it.
That's fine. All right. Let me see what I can do.
How many we got? How many participants have we got out there? At least 10. Oh, you're welcome, Jinx.
Get an internal chat up.
He's ready for a little quiz out there? Coffee time. Well, go make your coffee quick, Dave, because we'll be a quiz in a sec.
Yeah.
Wow, we're up to number 24.
Yeah. That's all right. Next week I should have a couple of quizzes.
Mm-hmm.
I've been pretty busy this week.
Yeah. Do you want to post those links to a few videos over in the Discord channel? Which one's the one I'd put it in? Oh, the homework one. Yeah. I'll put a couple of links to a couple of channels over in there. Yeah, homework. Yeah, I'll put them in homework.
All right. So we're ready, or we're still waiting for people? Or we're going to give people a chance to get coffees.
Dave was making a coffee. Miro said my brain is numb.
My brain is numb. Yep.
Dora said it's still a bit early yet. Maybe still a bit early yet. What time zone are you in? Oh, okay. Yeah, we're definitely on the wrong time zone stream at this time of day. Like, it's only 9:30 in the morning in Britain, and it's 5:30 in the AM in the USA.
Daylight savings ends here soon, doesn't it, Terry?
Yeah, Easter.
Yeah.
Friday or Monday?
Next weekend.
Yeah.
Next weekend, I think. No, it's always Saturday night to Sunday.
Oh, okay.
So it always changes.
We lose an hour or we gain an hour?
Oh, who knows?
Oh, one of those two. Yeah. Coffee, I'm still on the whiskey. Dave's back.
All right, let's get going then, hey? All righty, here we go. Question uno. When a radioisotope undergoes beta minus decay, does its atomic number increase, decrease, remain the same, or vary depending on the element involved?
Radioisotope.
Hmm. Do you know what an isotope is, Terry?
Or a beta minus decay or an atomic number? No. But I probably would if I was explained or shown. I'd probably find a comparison explanation that'll probably help me. But just as the word's written there, it makes it a bit harder.
Yeah, an isotope is a different sort of variant of a particular kind of atom. Like, for instance, normal hydrogen only has one proton in its nucleus, right? But if you stick a neutron in there with that proton, it's still hydrogen, but it's slightly heavier. And that's a different isotope of hydrogen. If you stick two protons in there with the one, two neutrons in there with the one proton, then it's still hydrogen, but it's even heavier. So it's a different isotope again. That's what they mean by isotopes. All isotopes of a particular element all have the same number of protons in the nucleus, but they have different numbers of neutrons. Yeah. And beta minus decay, what that means is that the nucleus chucks out an electron, a beta particle, which is an electron. It chucks out an electron. Now think of that. If you've got a particular charge in the nucleus and you chuck out something negative, what's going to happen? Any ideas? Is anybody out there?
Oh, we're getting it. We're getting it. We're getting a few. We're getting a few C's.
All right. Okay. Here is beta radiation decay. Okay. So think about it in terms of the charge that's in the nucleus. Okay, because the radioactive particle comes from the nucleus. So if you've got a particular charge in the nucleus and you chuck out something negative, that means you've got to leave less negative in the nucleus, which means it becomes more positive. Okay, so something has to change in the nucleus to be able to chuck that negative thing out. What happens is a neutron decays and it chucks out an electron, and that means what's left behind has to be positive. So it's a proton that gets left behind. So that means the atomic number goes up by 1. So beta minus decay results in things decaying up the periodic table. They go up the periodic table. Yeah, increase. Yeah,
increase.
Yeah, yeah.
That was throwing me off then. The beta minus, because you think minus it goes down. Yeah.
Yeah. But the beta minus means it chucks out a negative electron, a negative particle, a normal electron. Yeah. Okay. So the correct answer is that it increases. The atomic number increases because you're converting a neutron into a proton.
Oh, no, you got that.
Good. Well done. Okay. Question 2. What causes the gas tail of a comet to always point away from the sun? All right. Is it the solar wind, air pressure, centrifugal force, or gravity?
Oh. I'm thinking it's that one.
Are you?
but it doesn't sound right.
Oh yeah, I do, Carl. I try to kill your brains. This has never pretended to be an easy quiz.
But this question's not too bad.
Yeah, you should know this one. All right. But if you think about it, I mean, the comet is obviously in orbit around the sun.
Yeah.
So,
Always points away.
and we all know that a comet has two tails, doesn't it? All right. It has a gas tail and a dust tail. One of those tails points directly away from the sun at all times, no matter which direction the comet's moving in. That tail points away from the sun, whereas the other tail, the dust tail, curves a little bit, and that's a different thing. So we've got some answers.
Yeah,
we've got lots of A's, haven't we?
Yeah, that's what I was thinking of first. That was my first guess.
Yeah. Well, here's your diagram. All right. So you can see that it's the solar wind that pushes the gas particles so that the iron tail, not iron as an IRON, iron as an ION, ions, charged particles. The solar wind pushes them directly away from the sun. It's kind of like the light. The particles blow that tail away from the sun. Okay. Whereas the dust tail is a different matter. What that is formed by is the release of dust particles as the comet melts and releases dust particles. And then those dust particles themselves are in fact in orbit around the sun. Okay. And so that tail curves as the comet changes position in its orbit around the sun. Okay.
I'll say a flirt statement. How do you get wind in a vacuum?
It's the same as how you get wind on Earth. Particles moving. All right. There are particles being emitted by the sun all the time, and those particles moving away from the sun are literally what the solar wind is.
Yeah.
Yeah. So the correct answer was A, solar wind. Good. All right. Question 3. In chlorophyll-containing plants, what are the two products of green plant photosynthesis? So I think you all know what one product is, what plants produce, but what's the other thing that they produce? the ducktail.
Jeez. Mind blank.
Am I on the wrong track altogether, or do you want something that's more to do with?
Well, that's one of them, Terry. That's the obvious one that everybody knows about. But what's the other one? Remember, the question's asking for two products, Terry, not just one. Yeah. Peter Harrington, you need to go back to school to learn how to spell, dude. Sugar. Everyone knows the oxygen part.
Yeah.
Not quite right, Dora. The photosynthesis doesn't produce the cellulose. The other cellular processes within the plant produce the cellulose, but not photosynthesis. Carbon dioxide and water, no name of what is used in the photosynthesis reaction, but they're not the products. Ah, yes. Gas go down, go boom, boom. Has got the other one. It is, of course, glucose.
Oh, glucose.
Yeah, which is the sugar that Peter was trying to, the sugar that Peter was trying to say. I mean, that's the whole purpose. That really ultimately is the purpose of the plant doing photosynthesis, is to make glucose so that it can then use that glucose as energy in other processes within the plant. So, and as a byproduct, it happens to produce oxygen as well. But that's not the purpose of why it photosynthesizes. That just happens to be a byproduct of the photosynthesis. What it's really trying to get is the glucose. So oxygen and glucose was the correct answer there. Okay. Global climate change is being attributed to the atmospheric increase in what two gases produced by human activities? Now, this is a little bit misleading, this question, because there are more than two greenhouse gases, but these two are the two that contribute the most to the greenhouse effect. Which two are they? Are they ozone and methane, nitrous oxide and sulfur dioxide, methane and carbon dioxide, or ozone and carbon monoxide? Which of those pair constitute the two gases that contribute the most to global warming? Who's got the microphone up their nose? John?
Oh, that might have been me sniffing.
What?
Even though it's down on my chin.
Okay. It was you, Terry, was it?
I
Your
don't know.
nose hurricane.
I know I got the microphone down here on my chin.
Okay, most people seem to know the answer to this one. It is C.
Oh,
All right.
oh, I got that one right.
Methane and carbon dioxide, or cow farts, yeah. But the biggest contributor is, of course, carbon dioxide. And then the next biggest contributor is methane.
One theory I had about methane a while back, I don't even know if I've ever picked it up on a TV show about the dinosaurs and all that sort of stuff, is the methane that they produced, what effects that would have had on the atmosphere.
Well, it's not just the methane that's produced by animals like cows farting and stuff like that. It's also all the methane produced by decay of vegetable matter in bogs and swamps and stuff like that as well. That's a big contributor to the methane content that contributes to global warming as well. Yeah.
Our rubbish tip down the road collects the somehow it collects the gases coming off the dump underground, and it collects it to use it as fuel.
Okay. Yep. All right, question 5. What is the approximate weight in pounds of the atmosphere on a 1 square foot surface at sea level?
Oh,
so if you were to mark out a 1 square foot area at sea level, how much, and you were to weigh all the air that's above that 1 square foot, how much would it weigh?
Shit.
You can use your powers of estimation to come up with the answer for this one.
That's what I've been trying to think of how to...
Because everybody knows that it's 14.7 psi or pounds per square inch. Okay.
Yep.
Yeah. Okay. So how many square inches are in a square foot, Terry?
12 times 12.
Which is?
142. 100.
No.
100.
Close, but no cigar.
Yeah, I was just guessing.
144.
144.
Okay.
Yeah.
Yeah. So if you've got 144 of those square inches, and each square inch has 14.7 pounds, then you've got to estimate roughly what 144 times 14.7 is, or 15 roughly. How would you do that? If you multiply something by 15, then it's like multiplying it by 10 and then adding another half again, right? So if you had 15 psi, right, 144 multiplied by that by 10, that's 1,440. And then half of that's about, 720. So add that, and you get about 2,100 and something. So the answer is 2,100 pounds.
Oh,
Yeah.
that's close.
Yeah. And if that was a 1 square meter column, it ends up being about 10 tons of gas. Yeah, 10 tons of gas. So a square foot, it's around about 1 ton, just a bit under 1 ton, metric ton. But for a 1 square meter, it's about 10 tons of air that are above you. Yeah.
That would have been easier to calculate.
Yeah. All right. Question 6. A characteristic of the noble gases is that they all what? Do they all have 8 electrons in the outer shell? Do they all have low stability? Do they all form many compounds? Or do they all have filled outer electron shells? Noble gases. Do you know what the noble gases are, Terry?
The Queen's knighted them.
No, the noble gases, they're called the noble gases for a reason. And they include the gases like helium, neon, xenon, argon, krypton. Right? Not kryptonite, krypton.
Krypton,
Yeah.
yeah.
And they're useful in things like, for instance, argon. Where would you use argon, Terry?
It's a shielding gas for welding.
Yeah, why do you use it?
Because it displaces the oxygen around your welding.
Yeah, why would you want to do that?
Because of the when you're welding, you don't want oxygenated arcing in your welds because of the porosity of the molten part. I can't remember it off the top of my head properly.
It's basically because at high temperature the iron reacts with the oxygen to make iron oxide. In other words, you're including rust in your weld.
Yeah.
So it makes a weaker weld, right?
Yeah.
And the reason why you displace the oxygen with the argon is because why? Because the argon doesn't react, right?
Mm-hmm.
Yeah. So it's unreactive. So that kind of crosses out answer C, doesn't it? Because the noble gases don't form many compounds because they're fairly non-reactive. Having low stability is not right because that's implying that they are reactive and that they react with things, but they don't.
It's A or D, A or D.
So, and I've already mentioned that helium is one of the noble gases, but helium is the second element in the periodic table. It only has 2 electrons, so it can't have 8 electrons in the outer shell. All right, so that eliminates that answer. So by a method of elimination, you could have, D, that they have filled outer electron shells, and that's exactly what they are. All right, they have filled outer electron shells, and what you generally find is that elements that have, let's say you can fit 8 electrons in the outer shell, and if an element's only got 2, then it's going to try and want to get rid of those 2 to have a completely filled outer shell, which would be the next shell down. But if it's got, say, 6 in there, it's going to want to grab 2 from somewhere else to fill up that outer shell to make itself stable. Okay, so those are the reasons why elements react. But if it's already got a full outer shell, it's neither going to want to give any away or grab any more, because both of those things will result in an incomplete outer shell. And so that's why the noble gases are so stable and unreactive, because they have a completely filled outer shell. So the answer is D, they have filled outer electron shells. Good. Question 7. Mendeleev proposed the existence of an unknown element that he called eka-aluminium. Aluminum. The element is now called what? Okay, so when Mendeleev made the periodic table, he looked at the properties of various metals and he arranged them according to their properties, and he noticed that there were some gaps in the periodic table. And so he used his periodic table to predict where there should be some new elements that hadn't yet been discovered. And he even predicted what their properties would be. Okay. And so he predicted this element, which he called Eka aluminium or Eka aluminum. And when it was discovered, it was given another name. It wasn't called Eka aluminum. It was called something else. Who knows what it was called? Was it called magnesium, silicon, gallium, or germanium? He also proposed an element called eka-silicon as well. So it wouldn't have been silicon because they hadn't discovered silicon yet. I mean, they had discovered silicon, but it wouldn't have been silicon because they'd already discovered it. Sorry, the other way around. Yeah. Okay. Here is the answer in the clue. All right. It was gallium. Gallium is the actual answer. And here's his predictions. So Mendeleev's predictions and the actual properties for the thing. So he was pretty close in most of his predictions. He predicted it would have an atomic mass of 68, and it has an atomic mass of 69.72, but that includes all of the isotopes. Okay. He even guessed what density it would have and all sorts of other things. So he was pretty clever. All right. Question 8. Which of the following Saturnian satellites is known to possess an atmosphere? I'll give you the clue straight away because it doesn't really help you. Is it Tethys, Titan, Dione, or Mimas? So to have an atmosphere, it must obviously be a fairly big moon to hold on to that atmosphere.
We're getting some consistencies out there with a certain...
Yeah, they are. And so that would be the one to go with, wouldn't it?
Well, that's the only one I've heard of. I don't remember the other one.
Yeah. Yep, that is in fact correct. It's Titan. Yeah. So it's one of the Saturnian moons which they really want to explore because they think there might even be the possibility of maybe there being some life there.
And its mass to support a gravity to support an atmosphere as well.
Yeah. Okay. Question 9. In studies of the human body, which of the following terms is used to describe a very rapid heart rate or pulse rate? Is it bradycardia, tachycardia, cardiosis, or myocardia?
I'm only going for that one because it's got that name in it. Oh, some people are going for the other one then. Okay. Unless they know about it. I've heard of it. Unless one of the other ones there is for a very slow heart rate or pulse rate.
Yes. Yep. One's for a very slow heart rate, and that's bradycardia. All right. Cardiosis is more like an infection of the heart.
Oh, okay.
Myocardia. Yeah. And the correct answer is tachycardia.
Okay.
That means a rapid heart rate. And it's not good because what it means is that the heart's flapping around so fast that it can't actually pump properly. And so it's a kind of a form of a heart attack. Yeah.
I think my mother-in-law got something similar to that a few weeks back.
It's
Similar
pretty
to
common. Yeah. Okay, question 10. According to the French scientist Buffon, the solar system formed when our sun did what? Right, the solar system. Was it formed when the sun was first formed? Or was it formed when the sun collided with another star? Or was it formed when the sun began to cool down? Or was it formed when the sun began to expand? This is according to, remember, the French scientist Buffon, not the modern day theory.
Okay.
So this is his proposal for how the solar system formed. What did he think happened? You're doing a lot of guesses today, Carl.
I was trying to even analyse your choices here to think. Now, what do you thought? It did that, or did it? Could it do that?
All right, time
Yeah,
for a
I'll
clue.
try. I was about to type, but I'm not looking. So now I can look at the clue.
Okay.
Well, I don't know. I was looking at the keyboard. What to write?
Yeah, as you see there, his full name was Georges Comte de Buffon.
Buffon.
You got to see, yeah. Buffhead. Yeah, so the correct answer was that when the sun collided with another star. Sometimes it's said that he proposed that the sun collided with a comet. So the correct answer there was 10. So do you want to stop there, Terry, or do you want to keep going with the other 10?
We can stop there for a minute, and we might do Blue's video now.
Okay.
Yeah, I went through all the others, eliminating, trying to think, how would he think at that one? How would he think that one? And then I thought, yeah, that's the only one I could think of. Yeah.
Well, at least it's not as outrageous as Velikovsky's theory, where the Earth was apparently born out of Saturn.
Oh, okay.
Or Jupiter, one of the others. Yeah.
There's a Lindsay theory for you.
I need to go and make a refreshment.
Oh, okay.
I mean, I can do it while I'm here, but I'd have to mute myself. So, do we want Blue's version of this video, or do we want the unedited version of Blue's video? Because he's put two of them. They might say other stuff that we can probably pause it on as well on the other one. And they both go for the similar time, because Blue's edited one goes for 12:30 and the unedited one goes for 19. So I think he's just downloaded it and then edited it. Yeah, but which one, Blue? The Blue's edited version of the one I think he talks, or he might talk in that one more. The unedited one. Yeah, that's what I was thinking, and then we can...
Yeah, we can do our own. Analysis of it.
Analysis, yeah. Okay. Grab that. That should be the right one. And already have it over there. Yeah. I've got no idea what the sound level or anything it is at the most.
Pretty good. Yeah, you
There
sound
we go.
good. Okay, here we go.
That are claiming that gases are not affected by a downward acceleration. While it is true that gas molecules, when you equalize from one tank to another, and you initially get that rush of gas molecules from a stored container into a vacuum, they will continue to bounce around and bounce and bounce and bounce all over the place. Eventually,
So Bob's bought into the bouncy ball theory of gas molecules. Now, it's already been demonstrated that you take the pressure adjacent to a vacuum tank, basically, and you remove the barrier, then it equalizes instantly. The bromine gas rushes in to the pressureless tank, and the only thing that changes is entropy. There's no energy transfer. There's no temperature, no nothing. Okay, but according to Bob, I guess they just keep bouncing and bouncing, and eventually there is a change in energy. Okay, not initially when everything rushes in, but eventually it does change. Come on, man.
even sometimes in the same place, right?
So Bob, does that, when you're sounding stupid, and I'm feeling pretty stupid at the moment, but does when you say everything goes down, do you mean gases as well inside this device?
Even gases will, yes, because if you have helium, and helium is the least dense gas we know, right?
Mm-hmm.
But even helium
No,
has to
it's
be,
not.
if it's going to rise, it has to float up on something, right? Well, if there's nothing to
What?
float up on, then what's it going to do? It's going to sit on the
Pause,
bottom.
pause.
Helium is going to sit on the bottom. Is that what I'm hearing? Helium is going to
Terry
collect
must be away.
at the bottom
Can't pause
Yeah,
it.
of a vacuum chamber.
making coffee.
Oh my
God damn it.
God. Are you kidding me? Another parlor trick.
We can't sort of comment unless you
Allow me
pause
to
it, Terry.
demonstrate.
Okay, helium balloons in a vacuum chamber. 3, 2, 1.
Okay.
It's a bit hard to comment on, and Terry, when it keeps playing.
I knew there'd be some wrongness there somewhere amongst that. I was listening and I'm going,
Well,
you're
there
going
was
to say pause any second now.
Yeah, well, yeah, there was a whole shitload of nonsense in there, but this garbage of him saying that the helium has to float up on something. No, that's not how gases work, Bob. Like, it's obvious that if you separate out pure samples of nitrogen, oxygen, carbon dioxide, etc., they all have different densities, and yet we find them mixed evenly in our atmosphere. Gases don't separate out into their individual layers, their density layers, Bob. So we don't have one gas floating up on top of another gas. What we have is the gas molecules intermingling with each other. Each gas in its own right forms what we call a scale height, a column that decreases in density as you go higher. And that scale height, the rate at which they decrease in density changes with each gas, but they all do that and they all mix together in the atmosphere. We don't have one gas floating on top of another gas unless they are significantly more dense, like sulfur hexafluoride and stuff like that. Then that sort of thing can happen a little bit, but eventually they do dissipate. because of the random motions of the gas particles. So there, press play.
Are they confused because we can collect gases in a concentrated form like helium and that hexafluoride gases, and then show examples of that, like with a balloon it can rise, and that hexafluoride, whatever it is, that can go in a container, and that's what I was wondering if they're confused with.
Yeah. But if you leave those gases there long enough, eventually they will dissipate. Okay, even though certain gases are more dense, like radon, for instance. Radon is a very dense gas, and it tends to pool on the floor of buildings and get trapped there. And that's one of its dangers because it's radioactive. But even then, it will have its own scale height. It will have its own density gradient with height. You won't find a layer of radon and then a layer of carbon dioxide and then a layer of nitrogen and then a layer of oxygen. It just doesn't work like that.
Well, the air we breathe is a mixture of different gases.
Yeah, right up to the top of Mount Everest and beyond. It's the same mixture of gases. Yeah,
but not the same concentration though. Different levels of gas.
Well, no, it's pretty much the same mixture, Terry, all the way up. It's only when you get to the extreme upper layers of the atmosphere do you start seeing a difference in the composition of the atmosphere. And that's where you see the tailing off of the scale heights. The scale heights become quite different up there. But you have to go extremely high for that to happen. Of course, you've got the ozone layer. That's got a different composition because of where the ozone's being formed by the sunlight and stuff. But for most part, the composition of the atmosphere is pretty uniform at all heights. Yeah, so there's a certain percentage of, like there's mostly about 21% oxygen, about 78% nitrogen, etc., all the way through the different layers. We don't find a layer of this gas and then a layer of that gas and then a layer of another gas. It just doesn't happen that way with gases.
Press play.
Yep.
This looks like an Action Lab video, is it? Like doing an experiment of some sort. I missed that bit. What they're doing here.
They've got two helium balloons in a vacuum chamber.
Oh, okay.
It's actually two side by side. So they've got a helium balloon in a vacuum chamber, and then they're going to pump the air out of the vacuum chamber. And of course, the balloon falls to the bottom, doesn't it? Because it's got nothing to float up on. There's no buoyancy there.
Right, yeah. Well, I could have predicted that.
Just gravity.
But Bob, of course, is going to misinterpret that, of course.
Oh, okay.
Yeah.
Notice the balloon expands in all directions.
Yeah.
And they wouldn't have started off with a lot of helium in a balloon because the balloon's going to expand anyway, so the concentration of helium in the balloon's going to be less pressure of helium or whatever.
I'm trying to turn it off right before they pop. Oh, that one fell. See? Stop floating.
There we go, yeah. I was completely wrong. The helium does go down in a vacuum chamber. Or does it? Okay, the helium's lifting capacity.
Or does it?
Has appeared to go down.
But is that brain leak talking?
Yeah, probably. Yeah.
That's
He's bound to get something wrong.
Yeah, brain leak. Yeah, he always gets things wrong.
Look at the helium. It is blowing every direction.
Blowing?
What?
Pause.
Yeah, I did.
It's not blowing every direction. It's not like wind, Brian. It's the gas molecules have kinetic energy, random kinetic energy in all directions, except there is a downwards bias to that. But they do have, they're moving at quite higher velocity So yes, they will go in all directions. Yeah, but they're not blowing.
Balloon is not sagging toward the bottom. I repeat, the helium is not sagging at the bottom. It will never go down to the bottom of a vacuum chamber. That is fucking retarded. The helium will blow in every direction. That balloon will expand. It's not pooling at the bottom. I understand they think that in their brains, but look at the balloon. The balloon is expanding in every direction. Just because the balloon went down, the helium did not.
Oh, Bob, thank
It
goodness
is
you're here.
expanding
Hold on, I think they're
more
watching
and more
Yeah, hold on a minute.
Can you
in
hear me?
Oh,
every
Hold on a minute.
direction.
He completely didn't make any sense, did he, by saying what he was
Well,
saying about the expanding?
Well, no, brain leak has actually got something a little bit right there, in that the helium molecules are going in all directions, and the balloon does indeed expand in all directions.
Yeah, that
The
part,
reason why it expands is because you don't have air molecules pressing on the outside of the balloon anymore, so you don't get that equalization of the force on both sides of the membrane, and so you've got more pushing on the inside, less pushing on the outside, so it's going to expand. And he's right in that will expand in all directions. And he's right saying that it won't pool at the bottom. So he has got something right, but I'm sure he's going to stuff up that little bit of brightness with something massively wrong in a moment. Surely.
All right. Was that it, Brian? Was that the...
So what this guy is doing, I've showed this before.
Okay, that was 4 minutes. Okay, we're good. All right, so we've had Bob himself join. Hey, what's up, Bob?
Can you guys hear me?
Yeah, you're a little low, but not too bad.
All right, I'll kick the volume up here. Hang on just a second, and I'll get back to you and explain to you why Brian is wrong.
Okay. Sounds good. All right. Anything to say about that, Brian, while we're waiting for Bob to get back on? Brian? No.
I would say that the helium balloon still's got some buoyancy in that the vacuum is not completely done, and that's why it's still stood up and it's not lying on the ground.
Okay, is this a little better, my volume?
Yeah, perfect. Thanks, Bob.
Much better.
Okay, cool. All right, here's the problem with Brian's demonstration. First of all, he's showing helium balloons, helium-filled balloons inside of a gas chamber. And so what's happening is, because of the fact that he's removing the external air component, the helium, being more buoyant, is expanding inside of the balloon because it's fighting to get outside because there is no pressure outside. But what I said was that the gas itself would settle to the bottom. So here's what's going to happen. So when those balloons burst, and you can't see this, and by the way, I made it.
Yeah, that's the bit that I was picking up on that I thought was wrong. The gas itself inside the balloon was at the bottom of the balloon. I thought the gas would still be uniformly in all directions in the balloon all the time, even though it's expanding from having no atmosphere outside.
Yeah, well, it will be. It'll be, it'll fill the balloon. It won't pool at the bottom of the balloon. Even if you make a high vacuum, it just won't do that. If you had sensitive enough measuring equipment and you were able to measure the density at the bottom of the balloon and at the top of the balloon, you would find a difference. But you'd need something very, very sensitive to do that. It's just not going to be measurable or observable on something as small as a balloon. But if you were to have a really giant balloon, like a kilometre high, you definitely would find a density difference between the bottom and the top of that balloon. Yeah.
I made a mistake. It is actually hydrogen that is the lightest gas, not helium. Irrelevant, though. It's, whatever. So when those balloons burst, the hydrogen, or helium, basically got rocket shipped all over the inside of that chamber, right? And they're bouncing around like a mofo, big time. And they're going to do that for quite some time because there is this elasticity to, the molecules themselves. But
Can
after
I
a while,
just-
no, you can't. After a while, conservation of energy is going to take place, and that those gas molecules.
Pause. What does he mean? Conservation of energy is going to take place?
Yeah, that's
Conservation of energy. Conservation of energy is a thing that happens all the time, Bob. No matter what, we have conservation of energy. Energy doesn't get destroyed or created. We always have conservation of energy, right? If we're talking about a closed system, all right? So energy, providing we're not taking energy out of the system or putting energy into the system, we have conservation of energy. So he's completely wrong in saying that conservation of energy is going to take place, and he's going to say that the molecules will slow down because of that. That's just completely false thinking. It doesn't work like that. And the collisions between the gas molecules, the whole one of the assumptions of the kinetic theory of matter is that the collisions between the gas molecules is elastic, meaning that no energy is lost in those collisions. It just you can transfer energy from one molecule to another molecule, but we don't lose any energy. They don't slow down overall. If one slows down, the other one has to speed up. All right. So you can transfer energy from one molecule or one atom or particle to another, but the total amount of energy in all of that remains the same. Bob,
I've got a couple of questions. That video with the vacuum chamber, was there 2 helium balloons inside the same chamber?
I'm not sure.
And did the balloon that, when they stopped it, did that balloon fall or did it burst?
I think eventually it burst.
Oh, okay. I didn't see.
But initially it fell.
Yeah, that's what I thought. Yeah.
Are going to slow down. Now, in order for the gas molecules to rise, they have to be buoyant in contrast to something else. Well, there is nothing else inside of that vacuum chamber. Therefore, gravity.
No, he's completely wrong there. Completely on the wrong track. They don't have to have something else to support them. All they have to have is kinetic energy, right? And they collide with other gas molecules, with the walls of the container, and all of those collisions are elastic collisions. All right. And so if a gas molecule is going upwards, yes, sure, it's going to be affected by gravity, which is going to pull it back down. But it's going to eventually bounce off the base of the container or bounce off of other molecules, which are at the bottom there too, and be deflected back upwards. So you're going to get this filling of the container with a density gradient within the container. Okay, so you will have a higher concentration of molecules or atoms near the bottom, but they still will have enough kinetic energy to be able to fill the entire container.
Gravity or the downward acceleration is going to take its toll on them, and they are going to sit on the bottom. How do I prove that? Well, look at Earth. Look at Earth, right? Why do we have a gas gradient on the Earth? The reason is because we have all these different gases, and
is that what you mean by we don't actually have a gas gradient in the atmosphere? We're talking about that.
Well, we do have a gas gradient in the atmosphere, and Bob has just destroyed his own hypothesis here by using the Earth as an example. We don't see the gas molecules in the atmosphere slowing down due to his so-called conservation of energy bullshit, and gravity affecting them and slowing them down. Because if that was the case, then they would all pool into puddles on the ground. But that doesn't happen, right? We have the kinetic energy of the molecules is solely determined by their temperature. Okay, nothing else contributes to that. And so a gas at a certain temperature will have a certain amount of kinetic energy, regardless of how long it's been there or how long it will be there. It will still have that kinetic energy because all of the collisions are elastic. In other words, no energy is lost in those collisions.
the downward acceleration is pulling them down. Therefore, at sea level, you have 14.7 psi. In some places that are below sea level, it actually goes up to about 18 or 19 psi. When you get up to 50,000 feet, it goes down considerably lower than that. There is a gradient.
You to watch.
Because the downward acceleration is pulling down on it. And that's exactly what is happening to that helium. And I guarantee you that after that helium exhausts and succumbs to entropy, essentially, those gas molecules are going to sit on the bottom of that gas chamber. And there are ways to prove that as well. So there's how you're wrong, Brian. Sorry,
So
buddy.
your claim is
Bob,
that eventually
Bob,
the
can I
helium
just get in there for a sec, please?
Hold on, guys. He just addressed Brian. If Brian's there, let's let Brian.
Yeah,
respond.
if I could respond. Okay, if we kept watching the video, which we don't have to, I'll just give a quick explanation. I showed the balloons in liquid nitrogen and how they completely deflate. I don't think there's a gradient up into a complete void up there, but no, I think that the only way that the helium is going to pull at the bottom is if the temperature around it gets real cold and it liquefies, or something to that factor. Gas in a vacuum will always expand, and gas will expand in all directions in any chamber, but especially in a vacuum, and it'll expand without a change. The only thing that'll change is entropy. There's no energy. It'll always expand, and there's no energy loss, gain, anything.
Do you understand that I'm agreeing with you? I'm agreeing with you, but you cannot have perpetual motion of the gas molecules. Where are they getting the energy to do that? Eventually, they're going to run out of that kinetic energy, and they're going to settle on the bottom.
Pause. That's where his fundamental misunderstanding is. He thinks that in the collisions, they're going to lose energy. And so they'll run out of energy unless you somehow keep providing them with energy to keep bouncing around, which is just totally false. That's not how the kinetic theory of gases works. Like I said before, the collisions are elastic. There's no energy lost there. The only time you make them slow down is to take energy away from them, i.e. cool the gas down. And Brian's right. If you cool the gas down sufficiently, it will take up less volume, less energy. There'll be less pressure there. And eventually, if you cool it down enough and put it under a high enough pressure, it will liquefy. Okay? Brian's actually right there, and Bob is completely wrong.
Wow. It's not very often that he gets something sort of right.
But when you initially discharge into that vacuum chamber, you bet they're flying around like a mofo everywhere. But
Bob,
like
isn't that
anything
what
else,
condensation is?
I'm sorry? Say what?
That's slowing down. The condensation, isn't that the gases slowing down and sort of becoming water, losing a bit of their bouncing around?
That's what I was talking about.
Well,
that's what I was talking about. That has to do with temperature.
Are you talking about from the liquid nitrogen? No, liquid nitrogen is...
No.
All right, so...
Yeah, I wasn't quite done, man. I wasn't quite done with what I was saying.
Right,
but yeah, so there's no change. There's no change in energy or anything when gas moves into a low pressure or the gas swapped around. There's no energy change. It just is a change in entropy. And in a vacuum, I got a question. When would it when would the that's the, in my opinion, that's the parlor trick is in the ball model, they want to have their gas bouncing around and they want to have it go to the bottom they want it to fall down. But my question would be, when would the helium gas or any other gas fall down in a vacuum chamber?
Good question. When can we
as soon as it gets into a condition of entropy, as soon as it look, I don't know the exact time figure of how long they're going to bounce around, but guys, you do understand that things cannot maintain motion perpetually, right? Perpetual motion is not a reality, right? So eventually those molecules are going to slow down and they're going to stop bouncing around. And when they do, they are going to settle on the bottom. Why on the bottom?
Due to entropy, Bob. Entropy is what?
No, they're going to settle on the bottom because they have nothing to be buoyant upon. You have to have, now look, if there was air in there, then they would settle on top of that air, on top of that gradient.
Can't
No.
You're
I would say
roboting, Jeremy.
No, I can't.
Jeremy,
that is
you're
not going to
roboting
happen
bad.
at room temperature.
But if you're saying if there was helium gas in there, not in the balloon, that is, the helium would just mix with the air in there, wouldn't it?
Yeah, exactly. What Bob's suggesting is that if we had air in there, that the helium would settle on top of the air because it's being buoyant upon the air. That's what his suggestion is. And that's just not the way gases work. I mean, the mean-free path of the gas molecules is much greater than Bob gives credit for, I think. And so you're going to find that if you've got two different kinds of gases like that, that it's quite easy for the gas molecules to intermingle with each other and go past each other quite a number of times before they actually collide with each other. I mean, how would one gas support another gas? That literally means that the one kind of gas can't fit through the spaces in the molecules of the other gas for some reason. And the gas molecules generally in gases are too far apart for that to happen. And so for that reason, gases intermingle. They mix together, no matter what their density is, no matter what their type is or their atomic weight is, they will mix together. Yeah, he just doesn't understand what really happens in gases. And no, they won't lose energy. They won't eventually run out of energy and pool on the bottom, because if that was the case, all we'd need to do to get liquid air is to isolate it in a container and wait for it to run out of energy. and we know that's an absolutely ridiculous notion to suggest that would happen. I mean, where is the energy going, Bob? That would imply that to cool it down or for it to lose energy, that energy must be going somewhere. So what he's suggesting is that if we get a container of air and wait for it to settle on the bottom, where is that energy gone? It would have had to have gone into the walls of the container. And so we would have to observe the walls of the container spontaneously heating up, which is an absolutely retarded, ridiculous notion. We never see that. We know that heat doesn't flow like that. So he's completely wrong. He's not thinking about it rationally.
I agree with Brian. If it's at room temperature, then they're always going to get energy from the room because of the high temperature, and they're always going to bounce around.
Well, this seems like it would be a pretty easy thing to prove or disprove by experiment, Bob. Do you know of any?
Right, and I'll tell you how to do it. You don't even have to do an experiment. Just go down to your local gas store, buy a canister of helium, and before you walk out the door with it, shake it a little bit. You know what's going to happen? You're going to find that the helium has condensed and turned to a liquid at the bottom of that canister. Well,
wrong. I
was just going to mention something too about the containers that they put the gases in.
No,
as well.
You will not find liquid helium in the bottom of a container that you obtain from a shop. To liquefy helium, you have to cool it down to an extremely low temperature. You can't liquefy it just by compressing it like that.
Why did it do that? Because it can't.
Why is the spout not at the bottom,
Hold
Bob?
on, Brian, please stop interrupting. Let's not start the interrupting, guys. Please finish, Bob.
All right. Well, that's pretty much. Why is the spout not at the bottom? Well, I'll tell you what. If you go and look at Good Times for All the videos, he actually put a gas pressure gauge at the top and at the bottom of one of these gas canisters. And guess what? The gas pressure was higher at the bottom of the canister. Why? Because you have a downward acceleration that is adding to the force that's creating that pressure.
That was because he made he had a temperature change inside the canister.
He didn't do any temperature change. He had no temperature change.
Can you guys hear me?
Yeah,
yeah, we
Silent Zero. Hold on.
Good times for all when he had the bottom.
Hold on, Silent Zero. Go ahead, Jeremy.
Sure.
That'd be an easy experiment to do, wouldn't it? You just get two containers that have got the same amount of capacity and filled up the same amount. Put one upside down and one the right way up with a gauge on it.
Yeah.
Would the gauges be accurate enough or defined
that's
enough?
The thing. You'd have to have a gauge with enough resolution to distinguish between the very slight difference in pressure.
Yeah.
Sure. Good times for all video when he had the heat on the top and the cold on the bottom or whatever.
Oh yeah, that was the second part of it. He did another one where he put the cold on the bottom. Yeah, so absolutely that he could cause a condensation, also showing that. But otherwise, it will do it naturally as well.
He made a temperature. He made he made a gradient because of the temperature change. That has nothing to do with gravity.
On one video, yes, there's another one that demonstrates it all by itself.
Okay, so maybe you haven't seen that video, Jeremy, but yeah.
Look, guys, just use your common sense. Just use your common sense. Why would something remain in perpetual motion, or better yet, how does it remain in perpetual motion? And if gases always did remain in perpetual motion and were pressing up all the time against the top of the container just as much as they were on the bottom of the container, then how do we have a pressure gradient here on plain Earth, which is a flat Earth model? And mind you, I'm also postulating that we have a firmament over the top of us.
Yeah.
So I got one more thing to say. Oh, sorry. I got one more thing to say, Jeremy. One more thing.
There's a little bit of wrongness in there mixed in.
I know.
It always gets me beat why they use the word container in the wrong context of something being contained or something.
Yeah.
Yeah, a container can be an open container, can be a saucepan, can be a bowl. It's containing. Yeah. It contains something.
It's all y'all's, buddy. These are my closing statements. If he could demonstrate that, that'd be cool. But yeah, he just said how there could be a gradient, the temperature. But my final thing is air. Okay, it ain't just helium. You need all gases to pull at the bottom. Okay, and air will never pull at the bottom without temperature changes and all that stuff. It'll always stay pressurized until it slowly leaks out due to entropy or you have temperature variations. If you could demonstrate that, I'd be all for seeing it, bub. And I'd be convinced if you. I'm almost done, Bob. Almost done, buddy.
That's bullshit.
Almost done, buddy. Okay, let me finish. I wanted to say if you could show me a demonstration of it, that I would have a way more open mind toward it. If you could show me gas settling at the bottom of any chamber.
The problem is,
you know your butane lighters that you got, Paul.
Yeah.
And the ones that are see-through, that is. Now, is that gas? Yeah. That gas is liquid inside the lighter.
Yes, that's a different thing because the actual gas molecules are quite large. Butane is quite a large molecule compared to something like helium or oxygen or nitrogen. All right. I mean, a nitrogen molecule just has 2 nitrogen atoms in it, but butane has got quite a lot of atoms in it. It's quite a much larger molecule, and it also has some forces between the molecules. Okay, that cause it to condense into a liquid under a reasonable amount of pressure. So you put it under a reasonable amount of pressure, and those molecules come close enough together for those attractive forces to basically turn it into a liquid. So it's not just the molecules rattling around independently like in a gas anymore. If you get them close enough and slow them down enough, then the slight attractive forces between the molecules does have an effect, and it'll pull them together into a liquid, basically. Yeah, and that's what you see in the gas, the lighter. Yeah.
I'm not denying it. I'm just asking for a demonstration.
You are cocksure that this is the way that this behaves. You're not even thinking it through. Look at the evidence.
Yeah, but if you show me otherwise, I'll change my mind, Bob.
Yeah, let's see.
All right, you know what? I'm not really interested in convincing you. If you don't understand it, then I don't know what to say.
Hold on, Bob. I'm not quite sure that's fair. That's a fair position, Bob, because we are interested in experimental evidence, and a lot
then
of
why
us
doesn't he go out
are
and
you
do
know,
the experiment?
show me the proof. Your logic makes sense to me, and I'm trying to follow and make my mind up too. But I am also interested in seeing
So
the
why
experimental
can't you
evidence.
do the experiment and prove me wrong? Why do I have to prove myself right?
You're making a
He's the
positive
one
claim,
saying-
Bob.
That's not how
So
science
is he.
works, Bob.
Yeah, I
So
know.
is
I'm
he.
not convinced of his position either, though.
That's why.
And
Did somebody just yell out, "That's not how science works"?
Yeah.
Can I say
That's what I was
something?
laughing at.
Yeah, guys, good.
Can I say something?
Silent Zero, go ahead. You've been waiting.
Yeah, even if that's the case that the air or the helium sits in the bottom of the chamber, that's because that's the next denser thing that is available for the helium to sit on. If you insert another material that is denser, it's gonna take the helium up.
That's absolutely right.
You're proving
That's
actually
absolutely
you're
right.
proving, yeah, you're actually proving how density is the thing that moves things up and down, Bob. I don't know if you
Oh,
realize
you have
this.
got to be kidding me. So you're saying, let me get this straight.
No.
You're saying that it's sitting on the bottom because it's harder, it's more dense? Well, yeah, granted,
It's the
it is
next denser
dense,
thing.
but it's also part of the container. You've got to be kidding
Well-
me. There is no atmosphere in there. So there is no other molecules, so to speak of, to sit on, especially the gas variety. Now, if we put water in there, you know what? That helium and hydrogen would sit on top of the water. If we put carbon monoxide in there, it would sit on top of that.
How about liquid mercury? That's gonna bring even iron to the top.
Well, great. Then we are dealing with the buoyancy and density
Totally
argument.
irrelevant.
Yeah, totally.
In order for relative density to displace objects, there has to be a somewhat of a force that causes the displacement. And that force is brought about by a reaction to the downward acceleration that is constant on all things.
Why does there have
No,
to be
if
some
you're
force,
removing the density,
Bob?
if you remove the density of the container, that pretty much you're removing what we're trying to prove, right? The density is what moves things up and down.
I don't even know what you're saying. What are you trying to say? I don't even know what you're saying.
Yeah, you know, I've got no idea what he's talking about.
The density of the medium, you're proving relative density. Thank you.
Exactly.
Hold on. Let me ask a
go inside of
question.
a container? Are you guys smoking crack?
Let me ask.
No.
Hold on. Let me ask a question, Bobby. You said something. You said there has to be a downward acceleration. Isn't that what you said? Why?
Yes, and I cite that because of the example that I've given several times before. Let's go back to the density tower in the 0G plane. All right.
Okay.
What happened? When they were at normal 1G, the density tower organized, he could shake it up and it would organize and it'd line up perfectly with all the densities from bottom to top, from most dense to least dense, correct? Then they went to a 0G condition, right? And while in a 0G condition, which essentially is negating this downward acceleration, he shook it up. Guess what happened? Well, nothing would order. It wouldn't order anymore. Everything was just a jumbled mess. Then the pilot pushed it over. Don't say
I'll
no.
respond. Go ahead, finish, Bob.
I don't think he shook it up to
Then-
start with in that video. I think he was just trying to hold it steady, but because it went into 0G, it did shake a little bit. But I think he shook it up.
No, there is one video where he does shake it, Terry. Yeah.
Oh, okay.
The pilot pushed the nose over a little bit more and actually caused an upward acceleration. Now what happened? So he shakes it up. Then the density tower then reorganized with the heaviest gas or heaviest stuff at the top. It organized in the opposite direction. That is why I'm saying that you have to have a small bias there in order to displace and give buoyancy and relative density the opportunity to reorganize themselves. You can't do it without a force, guys.
All right.
You cannot things just don't do things just because.
No,
There has
hold
to
on.
be a force.
I'm going to respond. Okay. So, when a density tower is in the vomit comet, and
Well, that was it.
Yeah.
Yeah, that was the full version too.
It's astounding that Bob Nadell calls himself an engineer and he doesn't understand just fundamental concepts like this. I find that incredible.
Oh, Wally's out there.
Hey, Wally.
The Leo slap from today. Yeah, that was only recent, a couple of days ago. I think Blue mentioned that, about that. Okay, we don't need that anymore. We're coming up to 2 hours, so that's not too bad. Just check. Yeah, I was looking to see if you had anything recent, Wally, if I missed anything. Don't know if I'd seen it. A lot of people have been posting a lot of stuff. Too much. Wolfie had something. Hi, man, Dan. Oh, Flat Earther thinks he's called an idiot. But that'd be Flat Earth Friday. That'd be Simon Dan. Oh, here's a Where's Wally. What do you got here? Oh, the screw thing. Yeah, we'll play that. That was something that came up during the week. I have heard about that. Pause, Wally. Just a Leo from today. I mean a Leo. I haven't got anything recent today. Oh, here, yeah, that one. Oh, we got 2. Oh, Level Observer, that's the acronym, is it? Oh, we can do a double Wally if, because they don't go very long. Okay. How would you like a double Wally, guys out there? We'll do the screw one first. Get rid of that. Yeah, when you say Leo, I didn't know what you meant. Level Observer, yeah. Here we go, we'll do a Wally. This is the screw thing. Oh, got to share it in here. These guys.
G'day everybody, Where's Wally here? Well, Brandon and his crew, they went looking at the ISS today. Him and his crew, they think they're on a winner yet again. They play a video of an astronaut supposedly dropping a screw. Well, let's look what happens when you already are preconditioned to hear and see what you want to. Now, let's play Brandon watching it.
So he's unscrewing something and
Whoops.
whoa, what the fuck just happened there?
Why is he looking down?
If you listen to the audio, you can hear the screw drop.
Yeah, I got the audio up.
Oh, you can hear a screw drop. Yeah, right.
But definitely hear it go clink, clink. Just like the screw sounds when you drop it on Earth. Let's see. Oh, shit. The screw fell. Oops.
That's because they are on Earth, yeah.
Oh, man.
It's laughable, isn't it? Yeah, you got that natural earthy jerk and reach down to catch something when you got that natural jerky Earth-like reaction going on.
Yeah, what's up with that? They must have hit a patch of microgravity. That's probably what it was. Here we go. Oh, shoot. Just hit that patch of microgravity perfectly for that to happen.
I mean, have we heard any good excuses from the Globers on this? I can't wait. This is
No, Mike.
Come on.
Microgravity is supposedly what they're in when they're on the ISS, so they hit an actual patch of actual gravity. They're claimed to be in microgravity, free falling around the Earth.
They were passing over the Himalaya mountains at the time. A lot of mass there. Come on.
I guess it was macrogravity.
Yes.
The screw refracted down to the bottom, man.
No,
It dilated. It dilated. Yeah.
Now let's play the original, and we won't stop until Andreas puts the cover back.
Hier achter deze panelen wordt de urine opgevangen en gaat het doen. Deze moet ik vastmaken.
Are you saying something, Terry?
Sorry, I was muted. Even I can tell from watching this without even listening to any further, knowing what type of system they use on certain panels, what they would use in the ISS would be a quick release pin that you probably push, like spring-loaded pin, you push and turn it one way or the other and it'll just release. It wouldn't come out.
Zo. Hier is alle apparatuur waarin de urine opgevangen wordt. Er zitten speciale chemische stoffen worden toegevoegd. En dat komt dan in een tank hierboven. En voorbereide urine, die wordt weer gebruikt om weer gewoon drinkwater uit te maken.
You can even see the pins swinging left and right at the top.
Well, how about that? Brandon, he loves to say that we bring a pile of excuses, but this time all we need to do is to point out what he missed. No excuses needed. They were all so blind because they wanted to hear and see something, but they didn't stop and observe with a clear mind. Now let's look again, and I want to show you at 36:10 in the original, just a mere 35 seconds after the sound, the de-linked bolt's still there in the top right of the cover. Whoopsies! How about that? And that's before they get into their whole claims of editing and so forth. That's all that's needed to debunk this, but I think I will keep adding some cuts because there's heaps of dirt to come by the looks of it.
Let's make one thing clear, that this is not us saying that there's an ISS up there. We're saying this is done on a plane or wherever the hell it's done, and we caught them on...
You can even see a little arrow pointing, maybe it's something to either point at which direction to turn it even.
on their fakery. Let's make that clear now.
Yeah, absolutely. That's all we're saying is, hey, look at this. Why doesn't this comport with what we're told? Why is there a contradiction here when we see evidently something falling in what's supposed to be a 0G environment, and then we have 20 different people, nearly, a bit of an exaggeration, but not by much, come in and tell us different excuses why we didn't see what we saw.
Oh God.
That's ridiculous. I like that one though. I want to
Oh,
hear him.
I was referring to the. I was actually referring to the sound. Has anybody made an excuse for that when it hits the ground and clanks?
The sound of a screw dropping after we see the screw drop? Yeah, that's a good question.
And he even looks down at it. Okay, it drops and he looks down. Oh shit, it dropped. Where'd it go? It bounced around a little bit. Huh. Weird that. So come on, guys. Come and defend NASA. This is bad news for NASA. Awful news for NASA. Come in and tell us how we're misunderstanding watching a guy on a video drop a screw. Please tell us.
Can anyone calculate the speed that it dropped?
So let me just have a quick look at the actual sounds that Brandon says are the screw actually falling. There are only 3 sounds that show up. The first 2, Andre still has his hands clearly on the screw. The third one does not. It's only 1/3 of a second between the second and the third sound. So even if Brandon's fumbling theory was correct, really not enough time to get from there down to the ground. But of course, you know that's wrong anyway, because the screw hasn't gone anywhere.
We got our first excuse from the floor here. Well, we've had several from the panel, but Jose JG says nothing was dropped. Period.
Yeah, it's not a
Is
screw.
hanging
It's a
on
pin.
a thingy.
But it would make sense to put the little retainers on there so they're, you know, they take a nut or a bolt out and it doesn't fly around the room when they're working on stuff, you know.
Let's see what they're doing. Oh boy, this is 3 hours long. Surely they're not going to keep derping for 3 hours. Well, let's keep going. Oh, fantastic. Gem Panda is here. Maybe he can convince them.
Unscrew. Oh, what was that sound there? Huh. Hey, Gem, I'm glad you stopped by.
I wonder why you're frightened to play the whole clip. Why every time you played it, you've cut it off the instant he looked down. I wonder why you did that.
Well, I'm interested in the part where he unscrews the screw from the wall of the ISS, and it falls down and makes a noise. I'm interested in that part. Is there something later that's going to change that part of the video, or? So you hear it, and you see him look down. He unscrews something. You see him unscrew something. You hear something fall, and then you see him look down and look around for it. Am I an idiot, Jem?
Yes. I'll have one more go. If I can't speak, if I don't get away with it this time, if I don't get 3 full sentences out, I'm going. Okay.
Oh, big deal, Jim.
Come on, guys. Come on.
I want to hear
let him have a bloody go, for crying out loud, guys.
Oh shit!
Right, if you
Well, then
keep
you
playing,
need to talk instead of monologue.
sorry guys, it's worth a try.
No, you're good.
Clearly, it's not going to happen.
Come on now, let's hear the excuse. God damn it, guys! What the fuck?
Guys, come on.
We had him by the short fucking curlies.
And the way that this is always presented by flat earthers, you've been very careful to cut this video off at just the right moment. And you know
you want me to play it for?
You know very well
let's
that you
let
have.
it play, Jem, and let's see if that changes
Yeah,
when
let
we
it play.
watched it and heard it fall to the ground. Let's see if it changes
Try and
that
zoom
fact.
in on it.
All
Go
right,
ahead.
we're watching. Okay, so
And when
it-
when
did
he
it
puts it
change
back,
yet?
you can still see the pin.
No, not even Gem Panda can convince him. Well, let's see what other derp they get up to.
Does he put the screws back in after, or do we see that part?
You actually see them in the panel. They're attached to the panel.
Yeah.
They're like a sort of a
pin.
You know, like a sort of a butterfly, metal butterfly fastener type thing.
Well, that's been fun, guys. Brandon and his clown show, they never fail to entertain, do they?
Yeah. Are you gonna have a hard time convincing me that he didn't drop something in that video? But it's a good try. I mean, you got to make something up, right? You got to say something.
What this whole show demonstrates to us is that flatties are so willing to believe their own narrative that they pretty much keep patting each other on the back and working themselves up into a lather and just keep reinforcing the view over and over again. No one is thinking critically about it. Even when Gem Panda comes along, they just want to keep shouting him down.
Then what did we hear him drop?
I don't think you heard anything drop. Like I say, I think you heard the panel pop open.
The panel popping open sounds like something dropping to the floor and bouncing around.
That's what I was going to ask.
Well,
Thank you. Thank you.
You don't hear something dropping to the floor and bouncing around. You made all of that up.
You certainly do. We've played that multiple times.
Well, Brandon, I do have an ISS-related question. I keep asking you to have a look at the ISS live stream. I did the other day when you were in live stream, and you could have easily popped on at the end of the show. Look at your response. You really don't sound like someone who's open and looking and searching for the truth. Maybe you've already had a look and you don't know what's going on. But when you're doing your shows at the moment, the ISS is quite often almost right overhead. So for the next couple of days, you really should jump on this opportunity, Brandon, because you might not get another one for another 6 to 8 weeks. So while you're running your show, keep popping back in and having a look at the ISS live stream and ask people to comment. Anyone in the area below where the ISS is passing over, see if you can disprove what is being shown from the camera. The only problem is at the moment it seems to be doing a satellite handover right over the USA, so it seems to pop off at really when I don't want it to, but oh well, that's how it goes with the ISS. You have to communicate back somehow. Bye, guys.
Yeah, when I first seen it about the screw, I thought, oh, you've got to be kidding. They just cherry-picked that one completely, that one.
Yeah, that's what they always do. They just select the bit that they want, and like anything that contradicts them, they'll leave it out.
Okay. There's been other there's been that many others that they've shown live. They've shown feeds from the ISS of ones that we've done done the same thing. And then when you find the original video and played the whole lot of it, you go, yep, we've cherry picked that again.
Yeah.
I haven't heard any more about it lately, but yeah, I'm glad you picked up on that one, Wally. Oh, we'll finish off with a. Get rid of that. But the only other one I've got okay. To do with in the ISS, somebody's wrong again. Another level F observer one. We'll finish off with that. We'll finish off with the quiz, and that should bring us up to probably 3 hours then, Paul. Not too bad going.
Yeah, that's pretty good.
Okay, I'll get rid of that. We've got about 15 people watching. Is one and the rest of the quiz now, guys, out there? Any newbies turn up? Had's turned up. Who else turned up? Oh, besides Wally. 9 o'clock hero turned up too. Oh, I've got to change my thing for me battery for me. So if you're talking, you can get ready what you want to do. Got to change me headset battery.
Okay.
So what?
So we're doing the other questions, are we?
I'm back. What did I miss? Nothing? 11.
All right.
That
ready to keep going with the torture?
I think they are.
Okay.
Yeah, we'll watch the other one after the quiz. No.
Okay, question 11. The photoelectric effect is a demonstration of what? The wave nature of light, the particle nature of light, Compton scattering, or the continuous spectrum of radiation? Which one? Do you know your famous physics experiments or not?
No. I'm thinking of photoelectric effect.
Yeah. What is the photoelectric effect? Do you know what it is, Terry, or not?
No, but I'm having an educated guess. I'm going to go with an educated guess.
What, an educated guess as to what the photoelectric effect is or what it demonstrates?
What it demonstrates.
Okay.
Because I'm thinking, I've heard of photoelectric.
Well, okay, what I'll do is I'll describe the photoelectric effect to you, Terry, and then you can think, once you sort of have a bit of an understanding of what it is, then you might know what it demonstrates. So what the photoelectric effect is what they do is they have a glass enclosure that's evacuated, and they've got a bit of metal in there that's connected to an electrode, all right? And what they do is they shine some radiation, some light onto that bit of metal. And what they find happens is that light will eject some electrons from the bit of metal the energy of the light ejects electrons from the metal, and they collect those electrons and they measure how much energy they've got. And so they know exactly how much energy those electrons have got. And what they do is they shine different kinds of light. They shine different frequencies of light, and they find out that the electrons have more or less energy. And what they also do is they shine different intensities of the same kind of light. So for a particular frequency of light, they'll shine a weak source, a stronger source, and a very strong source of the same frequency. And what they'll find is that they get more electrons of the same energy. Okay, more or less electrons of the same energy. But for photons that are longer than a particular wavelength or lower than a particular frequency, they find that no matter how much light they shine on and no matter how intense the light is, you don't get any electrons being ejected from the metal at all. And so this is supposed to demonstrate something. So now that you know what the photoelectric effect is, what does it demonstrate?
Okay. From going from a few words that you said, I put that one in.
Let me see what you put. Right. You put... Okay. Well, that's pretty good then, Terry. Right.
But I don't know if I'm right or not. But I was just going by what words you were using to describing it, and I picked up on something. Then I thought, well, I wonder if that's to do with that.
What did you? Yeah, what did you pick up on, Terry?
Well, the particles to do with the electrons.
Okay. Yeah. What the photoelectric effect actually demonstrated was that that you could think of light as a particle that carries with it a certain amount of energy, and that if you use the different frequencies of light, like having a particle with a different amount of energy, the higher frequencies have more energy. All right. So it's like a particle with a higher energy. And so if you use those particles with a higher energy, then you're going to knock out an electron, and the electron's going to end up having more energy. All right. But if you use more of those particles, like increase the intensity, then you're going to knock out more electrons. But if you use particles that have less than a certain amount of energy, you're not going to get any electrons, because it takes some energy to free the electrons from the material in the first place. It's kind of like picking up something off the floor. If it's stuck to the floor, you've got to use some energy to get it off the floor, and then you can give it energy to make it move. And so you need a certain amount of energy to release the electron in the first place, and then any energy that's left over goes into its kinetic energy, its motion. And so what it showed was that you can think of light as particles with a certain amount of energy that carry a certain amount of energy. That's what the photoelectric effect is supposed to show. It shows the particle nature of light. So anyone that got that one,
yeah,
well done.
Yeah, well, I was glad you were explaining it, and then I was able to interpret different wordings that have other meanings or other variations of things, and so that helped me.
Yeah, they're saying some pretty correct stuff out in the chat there, like therefore light energy comes in quanta. Yep, that's right. A photon is a particle. Yep, that's the name we give to a particle of light, is a photon. Yeah. Okay, next question. 12. In a precise diet and nutrition study, you need to determine the average weight and average height of a group, each to a precision of 1%. The minimum sample size required is what? Is it 10 people, 100 people, 1,000 people, or 10,000 people? So you want to collect data from people, and you want to get an average of their height and an average of their weight. And you want that average to have an accuracy of about 1%. So how many people do you need to survey to get that accuracy? Obviously, if you get more people, you're going to get a more accurate estimate or a more accurate measurement.
Oh, you're going with that one, John. Okay. I was just thinking of 1%.
Hmm. Numbers, I don't do numbers. Yeah. 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 And for those that understand the maths of this, the accuracy is related to the square root of the number of people that you sample. So, for instance, if you sample 100 people, square root of 100 is 10, and 10 out of 100 is 10%. So you'll get an accuracy of around about 10%. If you only sample 10 people, the square root of 10 is about 3 point something. And 3 out of 10 is like 30 out of 100. So you're only going to get an accuracy of around about 33%. All right. So the more people you sample, the greater your accuracy, but it varies as the square root of the number of people. If you sample 1,000 people, well, the square root of 1,000 is like 30 something. So 30 out of 1,000 is only like about 3%. So you're still not accurate enough. If you take the square root of 10,000, that's 100. And 100 out of 10,000 is 1%. So that's how many people you need to survey. To get to an accuracy of 1%, you need to survey 10,000 people. Yeah, 10,000 people. Yep. There
Well,
you go.
John's
That's a
good.
bit of
John's good with
statistics
numbers
for you.
then, because he got it right.
He obviously is, yeah. All right. Question 13. Foods cooked in salt water compared to unsalted water will do what? Will they cook faster, boil at a lower temperature, not be affected in any way, or will cook slower because of the action of the salt?
Could be a couple of answers in this one, but thought it was that one is one of them. Yeah, I'm a toss up between the two, but I'll go with that one.
What one did you go with, Terry? Let's have a look.
Oh.
Okay. Yeah, so this has got to do with chemistry.
Yeah.
You need to know a little bit about your chemistry. And I think this kind of thing is generally covered in about year 11 or year 12 chemistry. So if you did senior high school chemistry, you probably would know the answer to this one. If you didn't, well then just experience at cooking would probably tell you the answer anyway.
Now hold on, Elmig said just asking Riley. Wait a minute.
Yeah.
No, he said, get me an egg stat.
Yeah. Yeah.
I knew those jokes had come out.
Yeah. This is a parts per million meter. I have no idea what it does.
No,
but...
it's got numbers on it, but I don't know what they mean.
Yeah, that's right. All right. Here is a graph that should tell you the answer. The boiling point change of water with sodium chloride, which is salt addition. So you can see that as you add sodium chloride, the boiling point actually increases. And if you make your water hotter, your food is going to cook faster, which is another reason why we use pressure cookers, because water boils at a higher temperature under pressure, and so your food will cook faster. So your food will cook faster in saltier water. However, your food will taste salty. So,
yeah, I was trying to think of the one where you had the boiling at the lower temperature. I'm thinking, how would that work? And I thought, no, that's something different.
Yeah. Generally, it's a principle of chemistry that if you have a boiling point of something and you add something else to it, in other words, you make it not pure, that the boiling point will then increase. So the correct answer was your food will cook faster.
Oh, what was the elevation? Yeah, that's what I was thinking, 9 o'clock here.
Yeah. Yeah.
Yeah, you didn't say that.
No. Okay. History. The Crab Nebula consists of the remains of a supernova, which was observed by who? Was it observed by Brahe in 1572? Was it observed by Kepler and Galileo in 1604? Was it observed by the Chinese in 1054 AD? Or was it observed by several ancient civilizations in 236 BC? The Crab Nebula. So it hasn't been around forever. Human history did actually observe the forming of this thing.
But with or without a telescope? Can't answer that yet. That'll be a clue.
Yeah. Yeah.
And we're getting a couple of C's.
We are, yes. Yep. And here you go. Cool science facts. The supernova explosion witnessed in 1054 AD, resulting in the Crab Nebula, was so bright it was visible during the day and night, and at night it outshined the full moon. So it was observed by the Chinese in 1054 AD.
Wow, I didn't think
Didn't need a telescope.
No, you didn't need one. And it was brighter than the moon.
Yeah, that's pretty bright, isn't it?
That is very bright.
Yeah.
Imagine if that was something that happened nowadays, which hasn't happened yet. Anything like
Oh,
that.
would have been, the astronomers would love it, wouldn't they?
Yeah.
Yeah. Okay. Question 15. Which of the following is the least effective technique used to sterilize something? And I don't mean to make, like cut your balls off. I mean sterilize something to make it non-infectious.
Least effective.
Least effective technique for sterilizing equipment. Yeah.
Oh, to me that's easy, that one, but I hope I'm not wrong. For the wrong reason. Because I know that one can be used for a certain reason, the one I answered, but for a different reason. For something else. What are we getting? D's? B? D, B's?
Getting B's and D's, yeah.
Yeah, I was thinking of the D, but I wouldn't call that, I didn't think that was sterilising something by filtering.
Well, that would apply to things like liquids, like sterilizing water and liquids and stuff. If you filter the particles or filter the bacteria and microbes out of it. Yeah. Okay, here you go. Here are all sorts of different sterilization methods and their advantages and disadvantages. Of course, you're not going to read all of that, are you? To find the answer.
Oh, thank you. And plus, it's in small print for me anyway.
And so, yeah, and so I would direct you right to the bottom down here where it says freeze drying. All right, freeze drying, low temperature, no structure property change, no toxic residue. That's an advantage. But one of the disadvantages of freeze drying or using low temperature, not effective. May affect the biochemical properties of scaffold.
Yeah.
So it's not very effective.
Well, the reason I picked the B for what I picked, because I'm thinking of the cold storage places where they store things to keep, and I'm thinking, oh well, that keeps things at low temperatures for longevity, but not for the other reason of the.
It doesn't really sterilize them, though. It just puts the thing on hold, sort of, doesn't it?
Yeah.
Yeah.
Well,
but once you thaw it out,
they do that. They do that in those laboratories. They put it in liquid nitrogen or whatever they put it in to keep things cold.
Yeah. All right. So the least effective was using cold. Yeah.
Molly said,
right,
"Can you read
question
out
16.
the question, please?"
Yeah, we do read the questions out.
Wasn't he listening?
Yeah. He must have been. Question 16. Which of the following causes the oblate spheroid shape of the Earth? Now here's an easy one.
Well, yeah, we should know this one.
Yeah.
We should know this one.
Is it A, the Earth's magnetism, B, the Earth's gravity, C, the Earth's rotation, or D, the Moon's tidal pull?
Oh, now you're confusing me. Not that one. It's that one or that one. I'm tossed up between two of them.
Oh, are you?
Yeah. Is it because of that, or is it because of that? Well, that means I'm tossed up with three of them, not not that one. Oh shit. We're only talking about this a couple of weeks ago. Yeah, I'm gonna have to go with that one for now. I may be wrong, but if not, it's the other one. Carl said A, B, C, D. You got to pick one, Carl.
Must be see your perspective.
You haven't.
I don't know. This is not much of a clue. This one, but I thought it was interesting. Which one is the oblate spheroid? The Earth is 12,714 kilometres at the poles and 12,756 at the equator. So one photo of the Earth is 1271.4 millimetres high and the other one 1275.6 wide. And the other one is 1275.6 high and wide. Which one's the oblate one?
I've got an actual satellite
You can't
image.
tell, can you?
I've got an actual satellite image photo that's actually it actually shows the difference.
Yeah. Yeah. That's right. And of course, we all know that it's caused by the Earth's rotation, isn't it?
Yeah, I know. That's what I was thinking. I'm thinking, no, that does that. The other one does that. No, that one definitely didn't do anything to do with that.
Yeah. Which two were you tossing up between, Terry?
Well, first it was the rotation, and then I thought the rotation and gravity, and I looked at the tidal pull, and I went, no, that only affects the tides. But then the magnetism, no, definitely. So then I thought, no, gravity, no, okay, rotation. I think it's the rotation.
Yep. Okay, question 16. Where are we? Question 17, sorry.
What happened to the answer?
No, I think sometimes what it does is it
pops it in.
Sort of,
yeah,
it's a bit of a delay in coming up. So I click again, and then it two things come in. So, okay, when a solid material is heated, it always what? Does it emit a discrete radiation spectrum? Does it glow red? Or does it emit a continuous radiation spectrum, or emits only visible radiation? So when you heat something, which of those options?
Yeah, but a solid material.
Yeah.
Solid material.
Yeah. Do you know what a discrete radiation spectrum is, Terry?
Yeah, sure.
No, do you know what it is or not?
No.
Because if you don't, okay. Discrete radiation spectrum means that it's a spectrum that's only got bits and pieces. Like it's got jumps. It's got this bit and then something's missing, and then it's got this bit and then something's missing. Then it's got this bit. So it's like lines rather than a continuous spectrum. Okay. You should be able to eliminate two answers pretty easily, Terry.
Well, I'm thinking of
Like-
metal. When you heat metal, it can do.
Well, I mean, like the obvious one, when you cook your food on the stove, it doesn't glow red, does it? If you got your food glowing red, you've probably heated it too much.
Okay. Well, that's why I couldn't figure out defining what the solid material is like.
Yeah. So I think you can safely eliminate B, can't you?
Yeah. Okay.
You know?
Okay.
Yeah. And you can probably eliminate D, right? Because we know that we can use infrared cameras to detect things that are emitting heat that we can't see visibly. And so some things emit radiation in the non-visible spectrum, even when they're heated. Okay. So it's got to be between A and C. And here is your clue. Continuous spectrum versus line spectrum or discrete spectrum. All right. So right down the bottom of that diagram, you'll see that a rainbow and black body radiation are examples of continuous spectrum, whereas emission spectra of hydrogen and absorption spectra of hydrogen are examples of discrete spectrum. Okay. And it turns out that a continuous spectrum is emitted by solid objects because that's what black body radiation is. Hotter it gets, the higher the peak of the frequency, and the higher the frequency as well. So it emits a continuous radiation spectrum. Question 18. Here's an interesting one. If you started with 100 grams of each of the materials below, and they all vaporized inside of an inflatable balloon, which of them would produce the largest volume balloon, assuming they were all at the same temperature? So if you took 100 grams of water and vaporized it into a balloon, okay, and then you took 100 grams of gasoline and vaporized that into a balloon, and then 100 grams of ethanol and put that into a balloon and vaporized it, and 100 grams of butane and did the same, which one would end up making the biggest balloon?
I answered straight away.
Ah, did you?
I've got a vague feeling I've heard this type of question before. Maybe not in the same format, but something similar to do with it.
Yeah, the reason why I've put a periodic table up here is because what will happen when you vaporize it, how much room it will take up, will depend on how many molecules are there. Okay. When a gas fills a certain volume at a certain temperature, it will create a certain pressure. The more molecules you jam in there, the higher the pressure, and so the bigger the balloon will be. All right? Because we know that under a higher pressure, a balloon will expand. So you've got to think about which one of those combinations will have more molecules. 100 grams of water, 100 grams of gasoline, 100 grams of ethanol, or 100 grams of butane. Okay? So if you know a little bit about chemistry, you know that water is H2O. It has 2 hydrogens and 1 oxygen, which give an atomic mass of what? 10, because oxygen is 8 and hydrogen is 1. Gasoline, however, is a hydrocarbon. It has carbon and hydrogens and a lot of them in one molecule. So it's going to be heavier than water. So for 100 grams of gasoline, you're going to have less molecules than you are with 100 grams of water. The same with ethanol, CH3OH. It's got a lot more things in it than water does. And so each molecule is going to be heavier than water. You're going to have less molecules in 100 grams than you are of 100 grams of water. The same with butane as well. All of those things, gasoline, ethanol, and butane, are bigger molecules than molecules of water. And so when you vaporize 100 grams of water, you'll end up with a lot more molecules than you will with any of those other substances. And so it will create the biggest balloon.
As in a hot,
The
as
answer
in a
is
hot air balloon.
water. Water, yeah. All right, so water vapor will create the biggest balloon out of those substances.
Yeah, I'm positive we've had a
Question
question
19.
similar to that one once before, but not the same
Yeah,
way.
we have. Yeah. Question 19. What are the only 2 metallic elements that end with the letter D? Think.
Well, obviously,
Metallic
I thought,
elements.
Yeah, I thought. So I'm on the right track with that one. No?
Yeah. Well, that's
No,
obviously one, isn't it?
Yeah, that's obviously the one. And then there's another one.
What's the other one? Yeah.
Yeah, shit.
Oh, there you go.
Oh, yeah.
Ah.
No, I'm not looking. I'm looking at my keyboard. I'm trying to...
Yeah, you got it. Terry's first.
I'm glad I watched these mine videos and all that stuff, because that was what was in my mind. Those two.
Yeah, well done, Carl. there's the list of metals. There are more than that, but that's got both of those on. Lead and gold are the two.
Yeah,
two
it's
that
interesting,
end with
those mine videos I watched.
Yeah.
Where they explore old mines.
Yeah. Last question.
Mm-hmm.
The angular distance between a planet and the sun, as viewed from the Earth, is called what? Is it called its angle of inclination, its angle of its elongation, its latitude, or its opposition?
Oh. I don't think I've heard words said for this in discussions with the Flurfers. Or no one's actually said it that I can remember.
Anglocentric quiz.
I'm probably wrong, but that one, I have heard of that.
No idea.
No idea.
So basically, if you were looking straight at the sun and then you had to go a certain angle away from that sun to look at the planet, that angle that you measure is called an angle. It's given a particular name. Yeah. Anyone who does a little bit of astronomy will know this, but and we do have a correct answer in the chat. And it's not John Stock's answer.
Okay.
Bugger.
that leaves me still. I'm still in there, John. I'm still in there.
Yeah.
If you're wrong, I'm still in.
I like the Elmig's answer, the angle of attack.
Yeah, I've seen that.
Don't look straight at the sun, no. I could look straight at the sun when it's set. The angle of the dangle. Here's a diagram which might help you, Terry. Get it?
Yeah, now I do.
Yeah. Yes, it's known as the elongation. Okay.
Oh.
And that's your quiz for today.
I don't know if they're getting better or am I just picking up on some of the things I've learned.
Well, no, you must be learning. You must be learning a few things, Terry.
Yeah, but I've got to retain them. It's different. It's different to get a question once every now and again and try to remember it compared to actually learning about the subject and then getting a question about the subject you've learnt.
Well, here's a hard one then for you, Terry. Is 0.99 repeating the same as 1?
Yes. I answered that quickly because I'm right.
Yeah. Can you explain why?
Can I explain why?
Yeah.
Because it's close to 1.
But if it's close to 1, does that necessarily mean it is 1?
Well, it's repeating. I just knew it was 1 because 0.9 repeating is close to 1. Or 0.99 repeating is 1.
Same as 1 what?
Same as 1 what, yeah. Okay, give me the reason. I probably do know it, but you have to refresh my memory.
Yeah, it's a common misconception that people think that 0.9 repeating is just a little bit less than 1, but it's not. It's another way of writing 1. It's exactly the same as 1. 1.000. Well, think of it. How do you write 1/3 in decimals? 0.3 repeating, right?
Mm-hmm.
Yeah, and if you multiply that by 3, you get 0.9 repeating, yeah?
Yep.
Well, isn't 1/3 times 3 exactly equal to 1? That's one way of explaining it, but there are other ways of explaining it too. Yeah.
Yeah, right, no name. You're going to try to sing it like that?
Yeah, I'd love to see it sung like that.
Yeah.
Oh well, that's it for tonight, hey?
Yeah, that's basically
Unless you've got something else for us.
We're up to 3 hours now already. I could finish off on a 4-minute video by Wally. That'll do it for tonight. Wally? Where's Wally? Where's Wally? Oh, there he is. Here we are.
G'day everybody, where's Wally here? Well, I've just watched Level Earth Observer do yet another bit of, well, what can I say? I never realised just how green our flat earth friends are, because man, are they into recycling.
I guess I'm not going to get a flip out of you guys, but I appreciate your time. Dr. Kate Rubins, Commander Victor Glover, thank you so much for your time. Be safe and Godspeed to you guys. Now, there they go. There they go. I love it.
Did you see it? I'd be disappointed if you didn't spot it. Turn the volume down. And let's watch this in all its pantomime glory here, as this cable to the microphone gets hitched on nothing. Here it comes. Get ready. She's desperately trying to unhitch it, but look, look, look. Caught on absolutely zero here. Look at the look in the eyes. It's like...
Yes, he's having another go at Victor and Kate this time. But what I really love about this guy is he has absolutely no idea that he's simply just proved that these guys cannot possibly be on a harness. Now, there are two things we know here for sure, that Kate Rubins, she has really long blonde hair, and Adam is an idiot. Now, what happens is when she does a bit of a roll, even though she's got most of her hair done up, anyone who lives with a person with really long hair knows there's always one or two little stragglers, and you happen to lean on them every single time. So clearly it got caught up and it pulled, and she disconnected it, and that was as simple as that. But if you're really observant and have a look at the path that the lead has taken, it pretty much wraps right around her whole body. There's no space that is not confined by that microphone lead. It goes right around everywhere, so if there had to be a cable somewhere, it would have caught up in it. It clearly didn't. All it managed to do was get caught up in one stray long hair out the back. Well, Adam, dear fellow, I hate to do this to you, but you're wrong yet again, mate. There's something you missed. Now, if you had gone back a little bit further, now maybe I am assuming you have watched this and you're just cherry picking as usual, but a little bit earlier, Kate and Victor were using the hands-free microphone, and they've put it down and they picked up the wired microphone. Now, I had noticed that the bit that stuck to the back of Kate's neck was a little bit of a lumpy part along the lead, and there are several of these things, and I couldn't work out why these things were there. Were they just poor sticky tape? So bear with me, because it's right about now that Adam has that sinking feeling in his stomach, because he knows Wally has found something that he himself has probably missed or purposely tried to hide. So, how are you feeling right about now, Adam?
I don't entirely know exactly what's going on.
Continue. But now watch what Victor does. Victor totally gives the game away, mate. And I think once you see what Victor does, you'll know exactly what happened to the lead on Kate and why it stuck to her. Poor Adam. This is so embarrassing for you, Adam. Look, I don't even think I'll even worry about the last two because, well, Captain Recycle's going to recycle, isn't he? When you haven't got much to say, mate, you really got to keep going back into the old stuff, don't you? When are you going to have a look at some of those new ISS footages? You seem to want to refuse to do that for some reason.
Wave goodbye to your families. Give them some love from the International Space Station. Go ahead as we say goodbye.
Well, thanks, Adam. That was super easy. Barely an inconvenience. If you keep popping up these easy ones, mate, we're just going to keep knocking them out of the park. So in summary, Adam, instead of proving that astronauts are in harnesses, you just really proved that using harnesses in space is a scientific impossibility. So thanks for that, mate. Well done.
Another cherry-picked bit of footage, as usual. There we go. You show them the evidence. Oh, there's one of your students. That's not the little duck, is it? The one that didn't grow very big? Doesn't know what to do. Stay. Stay. They're just sitting there. Got it well trained. That you're on camera, duck. Rubber ducky. Can we have the duck over for dinner? Oh, there you go. That's your lot for tonight, guys. I don't see it. What do you mean you don't see it? Ah, sorry. What duck? Oh, sorry, Dora. I didn't transition it over back to here. I don't know if you can hear me or not, Paul, but thanks for your help today. Thanks, John. Who do we have out there? Dave. Well, we have two Daves out there. We've got a Dave Cannabis and a Dave N. That's coming up. You should be seeing it now. Oh, wrong one.
Yeah, it's starting to peep now.
Yeah, I forgot to pin it. That way it's bigger. There you go. Now they can see it full screen. Okay. Hey Stevie B. Well, we're signing out now. Hi Tusk, you're a bit late. Thanks Carl, as usual. You're a regular. 9 o'clock hero. Subeagle, no name. I've got to scroll up. No name, Dave, Carl. Hads. Oh yeah, Dora. Elmigs. Trying to scroll up. If I missed anyone. 9 o'clock hero. All the regulars, no name. I already said you. Who else have I missed? Wally was here earlier. Oh, Fred Bailey was there. I can't go any further, so if I've missed you and you haven't typed in lately, you'll miss out on a calling you out. Shout out. Looks more like a chicken.
It is a chicken.
Oh, I thought it was a duck.
No, this is a chicken.
Oh. Well, I'm so used to your Harvard students being the ducks.
This is a silky chicken bantam cross.
Okay.
Yeah.
It's a very cross chicken.
Yeah.
That's looking for food, is it? Is that all they want to do? Eat?
Yeah, exactly.
Nothing on the screen, sorry. You won't find any food there. Oh, you want to send an email, do you? Nah. Didn't type anything out.
Whoa.
Whoa, what?
There you go. If it sees itself on the screen.
Yeah, okay. Let's see if it will. Well, I don't know how good's their eyesight at that age. Well, the microphone's there. You can take over the show if you want.
Yeah.
Oh, you're going to be quiet now, are you?
Yeah.
Give you the microphone, give you the keyboard. There's the screen. Off you go. I reckon your show will be a lot more entertaining than these Flat Earthers shows.
Yeah. How can you get that confused with a duck, Terry? Seriously.
Well, I only had it in the little window, and when I opened it up to the big window, I went, okay, maybe that might not be a duck. 'Cause I'm thinking of the big.
I'll show you one of the other ones next time. Some of the other ones have got feathers on their feet. It looks like they're wearing socks.
Wow.
This one hasn't, but the other ones have got like feathers on their actual feet. Yeah. You look like a cross chicken. Anyway, there you go.
Thanks for that. Well, you had me confused. I'm so used to your ducks.
It's got the punk hairdo on top too, mate.
Yeah, it has. Yeah.
I'll get back to the other view. There we go. Put you back up there. How did I get down there? Get back up there. I had me in the wrong spot. All right then. Thanks, panel. Thanks, Peanuts. We'll see you next time. I don't know when. I have to see. It's whenever Alan feels like it. It seems to be Saturdays that he's for now, but I'd like to do a Monday. If I can stream on a Monday, I'll ask him in the daytime, unless I'm busy this Monday. It's got a bigger pecker than me. Oh yes, Stevie B. Jeez. All right. If anyone wants to come over to Discord afterwards, you just know how to get there.
Yeah.
Alan's not here at the moment, Dory. He said he was going to try to drop in, but he didn't. So maybe next time.
He's got grandkids around, so
yeah. All right then. We're out.
That's Terry.
Good night, Peanuts.
Okay, what have I got to press here?